Welcome back, everyone, for another deep dive. This time we're diving into scalar conservation laws, but we've got a twist.
Yeah, that was
this time. So
yeah.
You sent us this research paper, and it dives into a special case where the flux function actually depends on whether the solution's gradient is positive or negative.
Right.
It's like having two sets of rules that govern how things flow, you know?
Yeah, and what's fascinating here is that this seemingly small change to make the flux dependent on the gradient sign throws a real wrench in the classical methods for analyzing conservation laws.
Right.
We're used to dealing with, smooth, predictable behavior.
Right.
But this discontinuity introduces a whole new level of complexity.
Yeah, so it's like our usual traffic flow analogy, just got a major upgrade. Instead of just car density affecting speed limits, now we're factoring in whether traffic is thickening or thinning out at a given point.
Exactly. And to make things even more interesting, this paper focuses specifically on what they call the stable case, where one flux function is always smaller than the other.
Okay.
And this leads to some intriguing dynamics with sinks forming at local maxima and sources appearing at local minima.
Okay, I'm already intrigued. So tell me about this paper.
Okay.
Who are the authors and what's their approach to tackling this problem?
All right, so the paper we're diving into is by Debora Amadori and Alberto Bressan from the University of L'Aquila in Italy, and Shen from Penn State University.
Okay.
And they use a two-pronged approach. So they explore both front tracking approximations. You can kind of think of this as tracking the evolution of sharp transitions in the solution and connecting those to solutions obtained via vanishing viscosity method.
So they're essentially looking at the problem from two different angles, hoping to find that common ground where these methods converge.
Precisely. It's like using two different lenses to examine a complex specimen, hoping to gain a more complete understanding by combining the insights from each perspective.
I like that analogy. Now let's jump into the mathematical nitty-gritty.
Yeah.
What's the fundamental equation that sets the stage for this whole exploration?
Yeah, so they start with a scalar conservation law represented by the equation what plus up plus AUX plus GUX equals 0.
Wow, that's a mouthful.
Yeah.
Can you unpack that for us? What are all those symbols doing there?
Sure, let's break it down piece by piece.
Okay.
U represents the quantity we're interested in.
Okay.
So like the density of cars on our hypothetical highway, FU and GU, are two possible flux functions, which represent those gradient-dependent speed limits we were talking about.
Okay, and that UC term is what's controlling the switch between those two fluxes, right?
Exactly. It's a step function that acts like a toggle.
Right.
If the gradient of U denoted by US is positive, meaning the density is increasing, it picks up. If the gradient is negative, meaning the density is decreasing, it switches to GU.
Okay, that makes sense. But why is this stable case where FU is always less than GU so important?
Right, so that condition is crucial because it leads to the formation of sinks at local maxima and sources at local minima.
Okay.
Think about it. If FU is always smaller than GU, then at a point where the density is at a maximum, more stuff will be flowing out than in causing the peak to decrease like a sink.
Right.
The opposite happens at a minimum. Stuff flows in faster than it flows out, creating a source.
Ah, I see. And they even illustrate this with a diagram in Figure 1 of the paper, right?
Yes. They provide a visual representation of the sink source behavior, which helps to solidify the concept.
Okay.
It's worth noting that they also briefly mention the unstable case, where FU is greater than GU.
Right.
But they leave that exploration for another paper.
A potential follow-up deep dive, perhaps. But for now, let's focus on the stable case. How do they actually go about solving this equation with its tricky gradient-dependent flux?
So they start with the front tracking method.
Okay.
The idea is to replace those potentially complicated flux functions, FU, with simpler piecewise affine approximations denoted by phi and g.
Okay.
Imagine replacing smooth curves with a series of connected straight line segments.
It's a way of simplifying the problem to make it more computationally manageable.
Exactly.
Okay.
Then at each point where the initial data has a jump discontinuity, they solve what's called a Riemann problem, which is a localized problem that helps determine how the solution will evolve at that discontinuity.
It's like breaking down a complex puzzle into smaller, more solvable pieces.
A great analogy. But here's a key difference from the standard front tracking approach.
Okay.
In this case, The solution's value can also change within those intervals where it has local maxima or minima according to specific ordinary differential equations.
So those peaks and valleys aren't just moving around, they're also changing in height over time.
Indeed.
That adds another layer of complexity.
And the paper meticulously outlines how to handle those evolving extrema, including how to restart the front tracking algorithm when those extrema merge, cancel out, or interact with moving fronts.
Right.
It's a very detailed and rigorous process.
Yeah, it sounds like they're carefully bookkeeping all the possible scenarios to make sure the method is robust. But do they actually prove that this front tracking solution is well-defined and doesn't lead to any mathematical contradictions?
Absolutely. They establish the well-defined nature of the front tracking solution,
Right.
ensuring it behaves nicely and doesn't break down in unexpected ways.
Mathematicians love their rigor. So what can we glean about the solution itself from this front tracking analysis? What kind of insights do they uncover?
Right. That's where things get even more interesting. They delve into the properties of the solution derived from this front tracking approach.
Okay.
One crucial finding is that both the L1 norm and the total variation of the solution actually decay over time.
Okay.
In simpler terms, this means the solution tends to flatten out and eventually vanish completely, as stated in proposition 3.1.
So even though we have these two fluxes causing all this, all the switching behavior,
Yeah.
the solution ultimately settles down and disappears. That's a bit surprising.
It is, and what's even more remarkable is that these properties hold regardless of whether the fluxes themselves are convex or concave.
Okay.
They also show, in proposition 3.2, that the solution has bounded variation for any time greater than 0. Essentially, it doesn't oscillate wildly. It changes smoothly enough to be manageable.
So it's a well-behaved solution, even though the equation itself seems pretty unruly. Do they connect this back to the original conservation law in any way?
Yes, they point out that this solution obtained through front tracking can be considered a weak solution to the original conservation law.
A weak solution. Does that mean it's not a real solution?
Not quite.
Okay.
A weak solution is a solution that satisfies the equation in a slightly less strict sense.
Right.
It's a way to broaden our definition of what we consider a valid solution.
Right.
Especially when dealing with equations that might not have classical, smooth solutions.
Got it. So they've explored the front tracking method in detail, uncovering some interesting properties of the solution in the process.
Right.
What's next on their mathematical agenda?
Now they shift gears and explore the vanishing viscosity approach.
Okay.
The idea here is to add a small artificial diffusion term to the original equation, represented by os, which smooths things out and makes it easier to analyze.
Right.
They then explore what happens as this artificial diffusion vanishes, hoping it converges to a solution of the original, more challenging equation.
It's like putting on a special pair of glasses that blurs out the sharp edges,
Right.
making it easier to see the overall picture.
Exactly.
Yeah.
And to build that bridge between the front tracking and vanishing viscosity approaches,
Right.
they introduced the concept of a regularized parabolic equation, labeled 1.6 in the paper.
So this is where they start to connect those two seemingly disparate methods, right?
Precisely.
Okay.
They emphasize the importance of the comparison principle, captured in equation 4.1, and the contraction property, equation 4.3, for this viscous approximation.
Oh.
These properties ensure that solutions behave predictably and don't become nonsensical.
Right.
Their ultimate goal is to prove that as the artificial diffusion vanishes, the solution of this regularized equation converges to the same solution they obtained through front tracking.
It sounds like they're setting the stage for a grand mathematical reveal.
Yes.
How do they go about proving this convergence?
So the heart of their proof lies in proposition 4.1, where they construct a special function denoted by WTX that sits remarkably close to both the front tracking solution and D, the viscous solution.
So this WTX is like a Rosetta Stone.
Yes.
Translating between the languages of front tracking and vanishing viscosity.
You could say that.
Yeah.
And to build this magical function, they cleverly utilize 3 specific types of viscous solutions. Viscous shocks. Near constant solutions at local extremas. And solutions obtained through a smoothing technique called mollification.
So they're using a combination of different tools to to craft this bridge between the two worlds.
Exactly. And that's where we'll pick up in part 2 of our deep dive.
Okay.
We'll delve into the details of these viscous solutions and see how they are woven together to create that remarkable function, WTX.
I'm already on the edge of my seat.
Yes.
Can't wait to see how this mathematical tapestry unfolds.
Picking up where we left off, remember that the researchers are building a bridge between two different ways of looking at this unique conservation law.
Right.
On one side, we have the front tracking approach with its sharp, discontinuous jumps.
Okay.
On the other side, the vanishing viscosity approach with its smooth, diffused solutions.
Right.
And that bridge is built with a special function, WTX, that needs to approximate both worlds remarkably well.
It's like trying to blend oil and water,
Yes.
but in a way that that actually works mathematically.
Exactly. Now, one of the key ingredients in this blend is something called a viscous shock.
So,
These are essentially smooth approximations of the sharp jumps we see in the front tracking solution.
okay.
Imagine taking those abrupt changes in car density and smoothing them out,
Was there-
making the transitions more gradual and realistic.
So if a front tracking solution has a sudden jump in car density, like a traffic jam suddenly appearing, the viscous shock would represent a more realistic scenario where the density builds up gradually.
Precisely. To understand these viscous shocks, the paper takes us back to the basics.
Okay.
They revisit the classic conservation law, oot plus FUX is 0,
Okay.
and its viscous counterpart, oot plus FUX equals zoo, which includes that added diffusion term.
Well, yes, the equation with that tiny bit of mathematical oil to smooth things out.
Exactly. They discuss the concept of a Lewis miscible shock, which essentially means the shock wave satisfies certain stability conditions.
Okay.
It's like a quality control check for shock waves,
Right.
ensuring they behave in a physically meaningful way.
So we're not just dealing with any random shock. It has to pass a mathematical inspection.
Right.
Yeah.
And what's really interesting is how they connect this Lewis admissibility to the existence of traveling wave solutions for the viscous equation.
Okay.
These are solutions that maintain a fixed shape as they move.
Right.
And as that viscosity parameter approaches 0,
Right.
they converge to the Lewis admissible shock solution of the original equation.
So it's like taking a blurry photograph of a moving car.
Yeah.
As the image sharpens, the car's true outline emerges.
Yes.
And that outline corresponds to the Lewis admissible shock.
A brilliant analogy.
Yeah.
But there's a catch.
Okay.
When trying to approximate those Lewis admissible jumps from the front tracking solution, these viscous traveling waves,
Right.
there's a technical hiccup.
Okay.
Just because a shock wave passes the quality control check for the piecewise affine approximation
Okay.
doesn't necessarily mean it passes for the original smooth flux function F.
Oh, that's a problem. So a shock might look good in the simplified version,
Right.
but fail in the real world.
That's the issue.
Okay.
To overcome this, they cleverly modify the fluxes of phys EG by adding small perturbation terms, mu-u2.
Okay.
This results in new functions, fu-u2 and upa, plus ou2.
So they're slightly tweaking the speed limits to make sure the shock waves play by the rules.
Precisely. They then prove in lemma 5.1 and corollary 5.1
Okay.
that with these modified fluxes,
Okay.
any shock that was admissible for the piecewise affine approximation
Right.
is also admissible for the modified smooth flux.
Oh, yes,
Like
sir.
adjusting the rules of the game to ensure fairness.
Right.
Right.
I love how they find these clever workarounds.
Yeah.
Now, how do they actually construct these viscous shock profiles?
So they start with the viscous traveling wave solution, UX,
Okay.
which, remember, maintains its shape as it travels.
Right.
They then smoothly truncate it to match the left and right states, U and U plus, of the shock wave.
Okay.
This creates a new function,
Okay.
which is smooth and coincides with the traveling wave solution near the shock.
Right.
And with the constant states, U and U plus further away,
Okay.
they lay out this entire process in equations 5.12 through 5.12.
So they're carefully shaping this traveling wave to fit neatly within the framework of the original problem.
Exactly. They then analyze how well this truncated profile actually satisfies the viscous conservation law.
Okay.
In lemma 5.2, they show that the difference between the time derivative of x and the spatial derivatives of x, those terms in the viscous conservation law,
Right.
is on the order of SU plus USAT.
So the error is small and controlled by that perturbation parameter we
Yeah.
introduced earlier.
Yes.
It's all coming together.
It is. Now, here's where things get even trickier.
Huh.
Unlike standard front tracking, where the states on either side of a front remain constant,
Right.
in our case, the solution can change over time within those intervals where it has local maxima or minima.
Right. Those peaks and valleys are actually changing in height over time.
Precisely.
How do they account for that in the viscous world?
They tackle this in 2 steps.
Okay.
First, they prove a technical lemma, lemma 5.3,
Okay.
which essentially provides a bound on the difference between the solutions of 2 ordinary differential equations. Okay. It's a mathematical tool they'll use later on.
A handy gadget in their mathematical toolbox.
Precisely. Then they use this lemma to prove another crucial result, lemma 5.4.
Okay.
It states that if we have 2 viscous shock profiles, U and V, with slightly different left and right states,
Okay.
the difference between these profiles is bounded by a constant times the difference in those left and right states.
So small changes in the endpoints lead to small changes in the entire profile.
Yes.
That makes sense intuitively.
It does. And they
So-
even refine this result in remark 5.1,
Okay.
showing that if we adjust the profile, U, to create a new profile based on those slightly shifted endpoints,
Okay.
the difference between ing and U is also small and well controlled.
Okay.
These lemmas demonstrate that these viscous shock profiles are stable under small perturbations in their defining parameters.
It's like saying if you slightly nudge the endpoints of a bungee cord,
Yeah,
the whole cord will adjust smoothly without going haywire.
exactly.
Yeah.
So far, we've covered viscous shocks in great detail.
Right.
Ready to move on to the next ingredient in building WTX.
Absolutely. What's next on the menu?
Now we need to figure out how to approximate the behavior of the solution near those local maxima and minima,
Okay.
where it's essentially constant but changing in time.
We're talking about those points where the car density is either peaking or bottoming out.
Right.
But those peaks and valleys are themselves changing in height over time, right?
Precisely. Remember, in the front tracking solution,
Right.
those changes are governed by specific equations.
Okay.
To capture this in the viscous world,
Right.
they introduce a special function Vx defined over an interval yh y plus h,
Yeah.
where y is the midpoint and 2 is the width.
Okay.
Right.
So this function Vx is going to help us model how those peaks and valleys change height in the viscous framework.
Exactly. They design Vx so that it satisfies a particular equation, 3h12, shown in equation 5.39. This equation comes from considering the viscous conservation law and matching the diffusion term, via,
Okay.
to the rate of change in the front tracking solution at those maxima and minima,
Right.
which turns out to be lineage 12 in this context.
So they're making sure the diffusion in the viscous solution mimics the rate of change we see in the front tracking solution at those specific points.
That's it.
Okay.
They introduce another clever function, zs,
Okay.
implicitly defined by zs, once s2, to construct Vx explicitly, as shown in equation 5.42.
It's like a mathematical treasure hunt
Yeah,
with one clue leading to the next.
indeed. They then present lemmas 5.5 and 5.6 to establish the key properties of this function, Vx,
Okay.
showing that it satisfies the desired equation and deriving bounds on its derivatives and integrals.
So they're making sure this Vx is well behaved,
Yeah.
does what it's supposed to.
Right.
But hold on, we've covered viscous shocks
Yeah.
and these near constant solutions. Isn't there one more piece to the puzzle?
You're right. For regions where the front tracking solution is smooth without those big jumps,
Right.
they take the original front tracking solution,
Okay.
modify it slightly for consistency,
Yeah.
and then smooth it out using a technique called mollification.
So they're basically giving the existing front tracking solution a makeover to fit in with the viscous crowd.
Exactly. They describe this process in equations 6.7 through 6.9.
Okay.
They truncate the front tracking solution, EX,
Okay.
to create EX,
Okay.
and then smooth it using a mollifier function,
Okay.
resulting in the final piece of their viscous solution, WKPX,
Okay.
in those smooth regions.
Okay, so now we have all three ingredients.
Yes.
We've got our viscous shocks, our near constant solutions at the peaks and valleys, and our smoothed out front tracking solutions for the calm regions.
That's right. But the real challenge is stitching these 3 pieces together seamlessly to create that smooth unified function, WTX.
I can only imagine how How intricate that process must be.
You're in for a treat. That's where we'll pick up in part 3 as we delve into the final steps of constructing this remarkable function and see how it ultimately bridges the gap between front tracking and vanishing viscosity.
Welcome back to our deep dive. We've been exploring this fascinating conservation law with its gradient-dependent flux, and it's been quite a journey.
Yeah, it's been amazing to see how the researchers use those two very different methods, front tracking and vanishing viscosity, to try and understand this complex equation.
Right, and remember, we spent the last 2 parts dissecting the individual components of that special function, WTX, those viscous shocks, the near-constant solutions at those local extremes, and those mollified front-tracking solutions for those smooth regions. We've got all the ingredients laid out. But now comes the real challenge, blending them together seamlessly to create that smooth, unified function that bridges the gap between the 2 approaches.
That's precisely where the authors take us in section 6 of the paper.
Okay.
It's a masterclass in mathematical craftsmanship. The first hurdle is ensuring that these different pieces fit together smoothly at the junctions.
Right.
Fortunately, at these matching points, denoted by UK, the different functions have some convenient properties. The viscous shock profiles and the mollified solutions have 0 derivatives at their endpoints, while the near constant solutions have derivatives equal to plus or minus epsilon, where epsilon is our tiny viscosity parameter.
So there's already some natural alignment between these pieces?
Yes.
But it's not a perfect fit just yet.
Exactly. There are still some kinks to iron out. To address this, they first create an auxiliary function, WTATX, which is essentially a patchwork of shifted versions of what those viscous shocks, near constant solutions, and mollified solutions, respectively. They shift these pieces so that the intervals where they are defined no longer overlap, but they carefully preserve the matching conditions at the newly defined endpoints, denoted as XKT. They describe this shifting process beautifully in equations 6.11 and 6.12.
So they're strategically rearranging the pieces on the game board, creating a continuous, but not necessarily smooth function, WTX.
Precisely. And as you astutely pointed out, continuity doesn't guarantee smoothness. The derivative, WXTX, could still be discontinuous at those junction points, XK.
Ah, yes, those pesky kinks we need to smooth out. And did they also mention a potential issue with periodicity?
You have a sharp eye. While our final function, WTX, needs to be periodic with period 1, meaning it repeats perfectly after every unit interval, this function, WTX, might have a different period denoted by...
So we have 2 problems to solve. Smoothing out the kinks and making sure the function repeats itself properly. How do they tackle these challenges?
They get even more creative. First, they divide the domain of WTX into 3 regions, plus T, where W is increasing, where it's decreasing, where it attains those local maxima or minima. Then they define a new function, plus TX, which is essentially WTX with an additional term that ensures the derivative, West TX, is either greater than or equal to epsilon or less than or equal to negative epsilon in those regions where W is increasing or decreasing, respectively. They define this new function in equation 6.13.
So they're forcing the derivative to be sufficiently steep in those regions. Which will help smooth out those kinks.
Brilliant observation. This modification also addresses the continuity of the derivative at the endpoints of those intervals, where WTX attains its maxima or minima. However, this fix introduces a new wrinkle. Win-hacks might no longer be periodic.
Oh, no. So close, yet so far. How do they resolve this periodicity dilemma?
They cleverly adjust the original front tracking solution, WinHex, by slightly increasing the size of each downward jump. They call this modified solution VTX, defined in equation 6.15.
They're tweaking the traffic flow again. But why does this help with periodicity?
By subtly increasing the size of those downward jumps.
Okay.
They ensure that the excess length introduced by making the derivative steeper in the increasing regions
Okay.
is balanced out by the increased length of those downward jumps.
Right.
It's a delicate balancing act to restore that perfect periodicity.
It's like adding a few extra cars to those thinning out sections of traffic to compensate for the speed up.
Yeah.
Amazing how they think of these things.
It is quite ingenious. And with this adjustment, the resulting constructed from Vdex now satisfies the periodicity condition. Finally, they simply rescale by the factor 1 to create our final smooth periodic function WTX with period 1 as shown in equation 6.16.
So they shrink or stretch the function to make it fit perfectly within that unit interval, like a mathematical paler.
A fantastic analogy. And remember that the whole purpose of constructing this function, WTX, was to prove that the front tracking and vanishing viscosity solutions converge.
Right.
And with this meticulous construction, they finally have the tools to do just that.
Okay, drum roll, please. How do they use WTX to seal the deal?
Section 7 is where they demonstrate that this painstakingly constructed WTX is indeed a very good approximation of the solution to the viscous equation.
Okay.
They leverage the properties of WTX and all those carefully derived lemmas to show that the error between WTX and the true solution is incredibly small.
So the difference between their handcrafted solution and the real deal is practically negligible.
Exactly. This means they can use WTX as a bridge between the front tracking and vanishing viscosity solutions.
Right.
Since WTX is close to both.
Right.
And also very close to the true solution of the viscous equation.
Right.
They can conclude that as the viscosity parameter goes to 0, the viscous solution converges to the front tracking solution.
It's like using a high-resolution camera to capture both a still image and a slow-motion video of a moving object.
Yeah.
As you zoom in, you realize they're essentially showing the same thing.
A perfect analogy. And that's the essence of their proof. They've shown that these two seemingly distinct methods, front tracking and vanishing viscosity, ultimately lead to the same solution for this intriguing type of conservation law.
Wow, what an incredible journey. We started with this seemingly simple equation, but ended up exploring this world of clever approximations, intricate constructions, and ultimately this beautiful convergence of ideas.
Yes.
It's amazing to see how these complex mathematical concepts can be brought to life and made understandable.
I'm thrilled you enjoyed the deep dive. What I find particularly fascinating is that this type of conservation law, with its gradient-dependent flux, might have applications beyond traffic flow.
Right.
Perhaps it could model other phenomena where the rate of change depends on whether a quantity is increasing or decreasing.
That's a fantastic thought.
Yeah.
And I'm sure our listeners will be pondering that as well.
Right.
Thank you for guiding us through this this complex yet captivating world of mathematics.
It was my pleasure. And remember, there's always more to explore in the vast universe of mathematics. So keep those deep dive suggestions coming.
Until next time, keep those minds curious and those questions flowing. Welcome to another deep dive today. We're going to be tackling some fascinating math.
Oh, yeah.
And, you know, our listeners are all math experts, right?
Absolutely.
So we're really going to get into the weeds on this one.
Yeah.
Today we're going to be talking about conservation laws.
Okay.
But with a twist.
Interesting.
And that is discontinuous, gradient-dependent flux.
Wow. Okay, so the way things are conserved can, like, suddenly change based on whether the quantity is increasing or decreasing?
Exactly.
Good.
And to really get into that, we're going to be dissecting a research paper called Conservation Laws with Discontinuous Gradient-Dependent Flux, the stable case.
Oh, okay.
Now,
well, that's a mouthful.
It is a mouthful, but, you know.
I think our listeners can handle it.
I think they can, too. The stable case that they're talking about in this paper means that one flux function is always smaller than the other.
Okay.
Which leads to some interesting behaviors.
Gotcha.
And you can almost think of it like a car on a hill. Like, as the car's going downhill, it accelerates, and then when it starts going uphill, it decelerates. It's that switching of the flux function.
Got it. That's a great analogy. So the flux function changes depending on, you know, the slope in that case.
Exactly.
Yeah.
Yeah.
Okay.
So let's just jump right in, shall we?
Let's do it.
All right, so page 1.
Page 1.
The abstract kind of sets the stage here.
Okay.
It's we're dealing with the scalar conservation law.
Yeah.
We've got that discontinuous gradient-dependent flux, and we're specifically looking at the stable case, where one flux function, we'll call it F, is always less than. The other one, which we'll call G.
Okay.
And they even give us a little bit of a sneak peek into their approach, mentioning a front tracking algorithm
Oh, interesting.
and convergence to a contractive semigroup.
Yeah. And those are really powerful tools when you're analyzing solutions to these kinds of equations. A contractive semigroup, basically. Guarantees.
Yeah.
Solutions exist, they're unique, and they behave in a predictable and well-controlled way.
Okay.
So you have this kind of mathematical guarantee of stability.
So we got existence, we got uniqueness. That's huge.
Yeah, absolutely.
And it looks like they're going to be connecting these semigroup trajectories to vanishing viscosity approximations.
Interesting.
I'm intrigued.
Yeah, vanishing viscosity is a pretty neat technique, right? It's where you kind of smooth out those abrupt jumps in the flux function, and it allows you to use tools from the world of smooth equations. And then the paper is going to explore how the solutions to those smoothed equations converge to the solutions of the original discontinuous problem.
That makes sense.
Yeah.
Okay, so moving on to page 2. They formally introduced the conservation law with the discontinuous flux.
Okay.
And they're using that step function, theta bar, to really capture that abrupt switch, don't they?
Yeah, they do. And then introduce the smoothed version of the step function, theta epsilon, along with a viscosity term in equation 1.6. So this is how they're going to start building that bridge between the smooth and the discontinuous world.
I see. And then figure 1 gives us a nice little visual representation
Yeah.
of the sinks and sources
Yeah.
in this stable case.
Yeah, and it's important to note here that they are specifically dealing with the stable case, where F is less than G for all values of U. There's actually a companion paper that explores the unstable case, where F is greater than G, and that leads to some very different dynamics.
Okay, so maybe a deep dive for another day.
Maybe.
All right, so page 3. They define what a weak solution to the Cauchy problem is.
Okay.
And it involves a few things, right? We've got continuity in L1 lock.
Yeah.
We've got a measurable function, theta, which captures the sign of the solution's gradient. And then they've got that integral equation 1.10.
Right. So a weak solution is basically a way to make sense of solutions that might not be perfectly smooth or differentiable. It's a way to kind of broaden the definition of a solution so that we can study a wider range of phenomena.
Gotcha. And they're focusing on spatially periodic solutions, which is L1 proof A for simplicity.
Exactly. And that's okay to do because the finite propagation speed that you get in these conservation laws actually ensures that the results hold even for solutions that aren't strictly periodic.
Okay, well, that's reassuring.
Yeah.
So let's turn to page 4. This is where we really get to the heart of the paper. Theorem 1.1. This is where they establish the convergence of solutions to that viscous problem. Equation 1.6 to unique limit. And that limit forms a contractive semigroup of weak solutions in L1.
Wow. This is like the foundation of everything they're doing, right? It's telling us that as we smooth out that discontinuous flux and let the viscosity vanish, the solutions, they converge to a unique and stable solution of the original problem. Cool. So this validates that whole approach of using vanishing viscosity to try to understand these discontinuous conservation laws.
Okay, so they've laid out the problem. They've defined their terms.
Yeah.
And now they've shown that a solution exists. What's next?
So on page 5, they give us a roadmap of what's to come. They're going to be exploring front-tracking approximations. They'll delve into the properties of that semigroup. And then finally, they'll connect it all back to those vanishing viscosity limits.
Sounds like a plan.
Yeah.
They also mentioned the challenge of defining what an admissible solution is in this context, which kind of hints at some of the subtleties involved in this uniqueness problem.
Yeah, that's always a tricky thing, right? It's like, how do you pick the right solution when you have a whole bunch of possible weak solutions, especially when you're dealing with discontinuities?
Right.
Yeah.
Okay, well, let's dive into some of the specifics here.
Okay.
Page 6. They introduce the front tracking algorithm, and to do that, they're going to be using piecewise affine flux functions, F sub nu and G sub nu, to approximate F and G.
Okay.
So they're going to approximate the initial data with piecewise constant functions, solve Riemann problems, and they can cleverly modify the solution on intervals where it hits local maxima or minima. And you can see that in equations 2.4 to 2.7.
Yeah, so this front tracking algorithm
Yeah.
is really powerful for constructing these approximate solutions. By breaking down the problem into these smaller, manageable pieces, it lets us study the really complex interactions between shocks and rarefaction waves.
I see. And then figure 3 on page 6 gives us a really nice visual, how dynamic this solution is, especially how that local maximum changes over time.
Yeah, great visual aid.
Yeah. So then on page 7, they talk about the 3 scenarios where the algorithm needs a restart.
Yeah.
So those are merging local maxima or minima, vanishing jumps, or interacting fronts.
Gotcha.
But they assure us that bounds exist so that the algorithm stays well-defined. It's really interesting to me how upward and downward jumps never cancel out in this setting. It's like those discontinuous fluxes really create these unique dynamics.
Yeah, absolutely. That's actually a direct consequence of that stable case assumption, where F is always less than G. In the unstable case, you can have cancellations. And that leads to some very different behavior.
Oh, okay.
Yeah.
So they need to make sure that their algorithm doesn't run into any roadblocks, right?
Exactly.
So that brings us to lemma 2.1.
Okay.
What does lemma 2.1 tell us?
Well, it guarantees that those intervals with local maxima or minima, they always maintain a positive length. And that's really crucial for the algorithm to actually work correctly.
Okay.
And you can see a nice visualization of this in figure 4.
Okay. So to establish that lower bound on the interval length, they're using the boundedness of the wave speeds and the fact that local maxima always decrease.
Right.
Which you can see in equation 2.11.
Yeah, and that all leads to that lower bound in equation 2.12.
It's beautiful how it all ties together.
It really is. It's a nice example of how careful mathematical analysis can really pay off. So
So then on page 8, we encounter lemma 2.2.
Okay.
And this lemma assures us that the front tracking algorithm only needs a finite number of restarts.
Okay, that's good. Right. You want to make sure that the algorithm is actually practical. It can't be restarting all the time.
Exactly.
Yeah.
But the proof of this isn't always straightforward. They point out that you need a very careful analysis when F and G are not convex.
Right.
In figure 5, this is a really good visual representation of this. It shows how a large shock can break up into these smaller jumps.
Yeah.
When F sub no isn't convex?
Yeah. The shape of the flux functions really plays a key role in the dynamics of the solution. When you have non-convexity, it can lead to these more complex interactions between the shocks and rarefaction waves. And the algorithm needs to be able to handle those carefully.
Right.
Yeah.
So then page 9, figure 6, emphasizes a really key observation. As that local maximum decreases, the number of new fronts generated remains bounded.
Wow.
And so that helps to control the complexity of the solution.
Yeah. And that same logic applies to local minima, which completes the proof of lemmas 2.2 and guarantees that finite number of restarts.
Wonderful. So we've made it to page 10, and they can finally celebrate the global definition of their front tracking approximation.
I did it.
All right, so what's next?
Well, now that they have this well-defined algorithm for constructing these approximate solutions, they're going to move on to analyzing their key properties.
Okay.
So that's where proposition 2.1 comes in.
Right.
It lays out 4 really important characteristics of these approximations.
Okay.
First, the L1 norm is non-increasing. Second, the total variation and the L infinity norm are also non-increasing. Third, we have the comparison principle. And fourth, the L1 distance between solutions never increases.
Well, so these properties are going to be essential for understanding how the solutions actually behave, right?
Yeah, absolutely.
So let's dive into the proofs.
Okay.
On page 11, they tackle property I, that non-increasing L1 norm.
All right.
To do that, they introduce an interpolated flux, F sub nu, which is defined at equation 2.15. And they make clever use of that step function, theta sub nu.
Right. So they partition the real line based on the sign of u sub nu, which you can see in figure 7. And then they meticulously analyze how that L1 norm changes on each of those subintervals. And equations 2.18 to 2.20 show how that non-increasing nature kind of emerges from that analysis.
It's incredible. And it's fascinating how they use the Lewis miscibility conditions.
Yeah.
And that crucial assumption that F is always less than G to establish this result.
Yeah. The Lewis miscibility conditions, they play a really key role here in selecting the physically relevant solutions from the set of all the possible weak solution. So in this case,
Yep.
they're ensuring that the solution is evolving in a way that respects the underlying physics of the problem.
Okay.
Yeah.
So then on page 12, they wrap up the proof of property I, move on to properties I and 3. And these properties follow pretty directly from the construction.
Yeah, the standard arguments
Yeah.
for comparison principles.
Right. So the comparison principle is a really powerful tool. It basically lets you compare solutions based on their initial data. So it tells you that if the initial data for one solution is larger than the initial data for another solution, then the solutions themselves will maintain that order for all time.
Wow, that's incredibly helpful for understanding the long-term behavior of these solutions.
Yeah, absolutely.
But what about property 4, that non-increasing L1 distance between solutions?
Right. So for property 4, they introduce these carefully crafted auxiliary functions, so W tilde plus and minus. And then they use the comparison principle to arrive at equation 2.22.
Yep.
And that sets the stage for the final part of the proof, which is on page 13.
So then on page 13, they complete the proof by showing that the term in equation 2.23 contribute non-positively.
Right.
Which leads to the desired result. Yeah, and figure 9 actually provides a really nice illustration of this. It visually reinforces the implications of equations 2.24 and 2.25.
Okay, so they've thoroughly established key properties of these front tracking solutions. What's next?
All right, so on page 14, they move on to remark 2.1, which emphasizes the flexibility that they have in choosing the initial data for the front tracking construction.
Okay.
So it turns out that it can be any function v bar in L1R. It doesn't have to be, just values in 2 minus nu z.
Okay.
So this highlights how general their approach is.
No, that's good to know.
Yeah. And then you use a limiting process to define a contractive semigroup S sub nu on L1R.
Okay.
And this prepares us for taking the limit as nu approaches infinity.
Right.
Yeah, so this is where they're starting to bridge the gap between those approximate solutions obtained through front tracking and the exact solutions of the original problem.
Makes sense. So that brings us to theorem 2.1, also on page 14.
Okay.
And this states that the L1 convergence of S sub nu results in a unique limit semigroup S with that contraction property.
Yeah.
Which you can see in equation 2.28.
Right, and this is a really pivotal result.
Right.
Because it confirms that as that approximation parameter approaches infinity, those approximate solutions are converging to a unique, well-defined solution of the original problem.
Okay.
And that contraction property ensures that things are stable and predictable.
So looking at the proof on page 15, they use Cauchy sequences, error formulas like equation 2.30 and density, piecewise, constant functions to establish convergence for general initial data.
It's just beautiful how they've addressed all of these technical details to make sure that the convergence and uniqueness of the solutions are really solid.
Yeah, it's impressive. So on page 16, remark 2.2 reassures us that these results hold true for the spatially periodic case as well, which justifies our focus on L1 per.
Right. And then they introduce proposition 2.2, which gives us a standard error bound for those front tracking approximations. You can see that in equation 2.32.
Okay.
So this is really valuable because it quantifies how well those approximations are capturing the true solution.
So we have a measure of the accuracy.
Exactly. And then on page 17, they continue. It's very detailed analysis, and they leverage the contractive nature of that semigroup and the properties of those piecewise affine flux functions to really derive that error bound in detail.
Okay, so we've established the convergence of the front tracking approximations, and we have a handle on the error. What's next in our exploration of this paper?
Well, now that they've laid all this groundwork, they're going to shift their focus to exploring the properties of those semigroup solutions. So on page 18, proposition 3.1 reveals that the L infinity norm remains bounded and that the solution eventually decays to 0.
Interesting.
So these are really important insights into the long-term behavior of those solutions.
So the proof focuses on controlling the measure of sets, where the absolute value of U sub nu exceeds a certain threshold. And that leads to the bounds.
Yeah.
In equations 3.1 and 3.2.
Right. So it's a very clever technique for analyzing those decay properties by bounding the size of the regions. Where the solution is large, they can guarantee that it eventually decays to 0.
And then on page 19, they point out that these decay properties are independent of whether the fluxes are genuinely nonlinear or not.
Right, yeah. So that highlights the robustness of their results. It's saying that this decay behavior holds regardless of the specific shape of those flux functions.
So the decay is going to happen no matter what.
Pretty much.
That's
Yeah.
fascinating.
Yeah.
So what's next in their analysis?
So they move on to proposition 3.2, which
Okay.
is this concept of locally bounded variation for that semi-group solution. And it's quantified by equation 3.4.
Okay.
And this property is going to be crucial
Yeah.
in establishing
Uh-huh.
the regularity of the solution.
All right. The proof on page 20 looks pretty intricate.
It is, yeah.
They're using the boundedness
Hmm.
of the L infinity norm,
Mhm.
the idea of finite propagation speed,
Right,
and a careful analysis
right.
of intervals where those local maxima and minima occur
Mm-hmm.
to derive a uniform bound
Mm-hmm.
on the total variation of those front tracking approximations,
It is.
which is shown in equation 3.6.
It's really a tour de force of mathematical analysis. They're carefully combining all these different properties of the solution to arrive at that desired bound.
Wow. And then page 21, they present proposition 3.3.
Okay.
This is kind of the grand finale
Yeah.
of this part of the paper. It confirms
Yeah.
that the semigroup trajectory does indeed give us a weak solution to
Nice.
the Cauchy problem,
Yeah.
satisfying definition 1.1.
This is where it all comes together. They're using that uniform bound on the total variation and the convergence properties of those front tracting approximations to establish those crucial integral equations, 1.9 and 1.0. And those equations demonstrate that their solution actually satisfies the definition of a weak solution.
This has been a fascinating journey. We've covered a lot of ground,
Yeah.
and I'm really eager to hear what comes next.
Me too. It's going to be exciting. All right, welcome back. We're diving back into those conservation laws with discontinuous gradient-dependent flux.
I'm ready for more. So last time we finished with that confirmation that the semigroup solution is actually a weak solution to the Cauchy problem. What's next?
So now they get into the spatially periodic case, specifically with proposition 3.4 on page 22.
Okay.
It says that in this case, the front tracking solution eventually converges to the average value of the initial data. It's equation 3.8.
So no matter what crazy initial data we throw at it, it'll all smooth out and just become a constant value.
Yeah, eventually. And it's all because of how the local maxima decrease and the local minima increase. Unless it's constant, it just leads to a contradiction.
Interesting. Okay, so everything's working out perfectly. But then on page 23, they give us this example 3.1. It's a weak solution, and it satisfies that entropy condition. But it's not one of the semi-group trajectories that we get from those vanishing viscosity limits. What gives?
This is where defining those admissible solutions gets tricky.
Right.
Just having the entropy condition isn't enough to say we've got the right solution. You can have multiple weak solutions that meet that entropy condition, but only one will be the one that makes sense physically, the one that comes from the vanishing viscosity.
So just because it's a weak solution doesn't mean it's the solution we want.
Exactly. Approximations.
Okay.
Still working with the spatially periodic case here, so we're looking at that parabolic equation 1.6.
We know this one has well-defined solutions, Ryan. Remember we had that comparison principle in equation 4.1 and the contraction property in equation 4.3.
Yeah, those are great.
Those were important to show that the total variation of these viscous solutions doesn't get any bigger over one period.
They really help to show how stable and well-behaved the viscous solutions are.
Right. And then on page 25, we get to theorem 4.1, which kind of brings it all together.
Okay.
So it says that as epsilon and delta get closer and closer to zero, the viscous approximations, which we called S epsilon comma delta, those converge to our semigroup S.
So those semigroup trajectories that we spent so long building with the front tracking, they are the limits of those vanishing viscosity solutions.
Exactly. That's what the theorem says. And it's really important because it shows that both approaches get us to the same answer. It's not like they're just mathematical tricks. They really represent what's happening with this conservation law when the viscosity goes away.
And it's the unique limit too, right?
Right. Only one solution fits the bill.
That's incredible. So what about proposition 3.3? It seemed to solidify that connection between the semigroup trajectories and the weak solutions to that Cauchy problem. Right, so that took us back to the formal definition with all the conditions. Continuity, that measurable function for the gradient sign, and that integral equation. And we saw how those front tracking approximations with all their convergence properties satisfied all of them.
Okay, so we had that challenging problem, a conservation law with a jumping flux. But with all the analysis, approximations, and math, we got to a semi-group of solutions.
Solutions that are based on both those front-tracking approximations and the vanishing viscosity approach.
It's amazing how much we can learn from this paper.
It really shows you how powerful math is, and it makes you wonder, how could we use this to understand systems of conservation laws where you have multiple quantities interacting?
Oh, yeah, where things get even more complicated.
Yeah.
It seems like we could get even more amazing insights that way.
Absolutely. And that's something to think about as we keep exploring and learning. But for now, we've got a solid solution for this conservation law, and that's something to celebrate.
All right, so here we are, the final part of our deep dive into conservation laws with discontinuous gradient-dependent flux, the stable case. It feels like we've been on quite a mathematical journey.
We have. Front tracking, viscous solutions, error estimates, we've seen it all. And now we get to see how all these pieces come together to finally solve the original problem.
I can't wait. So where do we pick up?
Well, we just finished talking about those error estimates, remember? That was all about showing we could construct an approximate viscous solution, W, that was like a mirror image of our front tracking solution, but still worked with the viscous equation.
Yeah, and we could shrink those errors as small as we wanted by tweaking those error parameters.
Yeah.
Talk about precision.
Exactly. Now, think back to our goal, proving theorem 4.1. That was the one saying those viscous approximations so converge to our semi-group S as R and dou go to 0, and proposition 4.1. That was the key.
It was like our bridge between those two worlds, the front tracking approximations and the viscous solutions.
Exactly. By showing we could find a viscous solution that was practically hugging a front tracking solution, we proved that in the limit, they had to be the same thing.
So theorem 4.1 basically says those semi-group trajectories, the ones we built so carefully with the front tracking, those are the true, unique limits of the vanishing viscosity solutions. Pretty amazing.
It is. It means they're not just some mathematical curiosity, but they really do represent what's going on with this kind of conservation law when viscosity becomes tiny.
What about proposition 3.3? That seemed to nail down that connection between the semi-group trajectories and the weak solutions to the Cauchy problem, right?
Absolutely. Remember that whole formal definition with all the conditions. Continuity, that function for the gradient sign, the integral equation. Well, we saw how our front tracking approximations, the way they converge and everything, ended up satisfying all of those conditions perfectly.
So we came a long way. Started with a tough problem, a conservation law with that crazy jumping flux, and after all that analysis, those clever approximations, and some good old-fashioned mathematical creativity, we got a nice semi-group of solutions.
And those solutions capture the whole problem, combining both the front tracking and vanishing viscosity approaches.
It's incredible how much we were able to learn from this paper, not just about this specific type of conservation law, but all the mathematical tools and techniques we used along the way.
Absolutely. It makes you wonder, how could we extend this to understand those systems of conservation laws where you have a bunch of quantities all interacting and evolving together? Think how much more complex and how many more fascinating insights we could uncover.
It's like an invitation to dive even deeper into the world of mathematical analysis. Who knows what amazing discoveries are waiting out there?
For now, we can celebrate the fact that we've tackled this challenging problem and arrived at a solution. It's a testament to the beauty and power of mathematics to help us understand the complexities of our world.
Well said. Until our next mathematical adventure, keep exploring, keep asking questions, and keep that curiosity alive.
Welcome to the deep dive. Today, we're diving deep, into this fascinating world of conservation laws, but with a twist.
Oh.
Yeah, we're dealing with discontinuous gradient-dependent flux.
Okay.
You've sent us a research paper
Right.
by Amadori, Bressan, and Shen.
Okay.
It's called Conservation Laws with Discontinuous Gradient-Dependent Flux. The stable case.
It's a dense one.
It's a dense one. We're going to try to unpack the key findings and mathematical machinery.
Yeah.
And really make sure you grasp the significance of this work.
It's definitely a challenging paper.
Yeah.
Dealing with a rather specialized area of conservation laws.
Right. It's not your everyday traffic flow problem.
Yeah.
To kind of set the stage, though, imagine you're modeling traffic.
Yeah.
And the way drivers behave changes drastically depending on whether they're accelerating or braking. This paper explores a similar concept, but in the realm of mathematical equations.
Okay.
We're talking about scalar conservation laws where the flux function,
Right.
which dictates how Quantities like traffic density evolve,
Okay.
can switch,
Interesting.
depending on whether the solution is increasing or decreasing.
That's a great analogy.
Yeah.
And what makes this paper particularly interesting is that it focuses on the stable case, where one flux function is always less than the other.
Okay.
This leads to some intriguing phenomena like sinks and sources popping up in the solution,
Oh, wow.
which we can delve into later.
Okay, so let's dive into the paper itself.
Sure.
Where do these mathematicians begin their exploration?
They start, as most papers do, with an abstract.
Okay.
Here, they lay out their goal to understand the behavior of solutions to this particular type of conservation law.
Right.
They also highlight the key mathematical tools they'll be using, namely the front tracking algorithm and vanishing viscosity approximations.
So they're giving us a roadmap of their approach right off the bat.
Yeah.
Let's talk about the introduction next.
Okay.
What's the core concept they're grappling with?
In the introduction, they lay the foundation by presenting the conservation law in equation 1.1.
Okay.
This equation looks like this.
Oh.
2 plus FU equals $zeros.
Right.
This equation captures the essence of a scalar conservation law,
Oh, wait.
where U represents the conserved quantity, T is time, X is position, and F is the all-important flux function.
Okay.
Now, the twist here is that this flux function, F, isn't your typical smooth function.
Right.
It actually switches between two different functions,
Okay.
F and G,
Right.
depending on the sign of the solution's gradient, UX.
So if the solution is increasing, we use one set of rules, and if it's decreasing, we switch to another. That's where the discontinuous gradient-dependent part comes in.
Exactly.
Okay.
And to tie back to your traffic analogy,
Right.
imagine F governing the behavior of accelerating cars,
Okay.
and G dictating how braking cars behave.
Okay.
This switching captures the abrupt change in dynamics based on the traffic flow's direction.
That's a pretty intuitive way to understand it.
Yeah.
The introduction also mentions a stable case where S is always less than G. Why is that distinction so important?
The stable case leads to some unique mathematical properties that make the analysis both challenging and fascinating. For instance, it introduces these sinks and sources in the solution, which behave like points where the traffic density either disappears or spontaneously appears.
Wow.
The authors hint that this stability condition is key to proving the convergence of their approximation methods to a unique solution, which is their ultimate goal.
All right, so we've got our equation set up, we understand the significance of the stable case,
Right.
and we know the authors are aiming to prove the existence of a unique solution.
Correct.
What's their first move in tackling this problem?
They dive straight into the front tracking algorithm in section 2.
Okay.
It's a powerful tool for approximating solutions to conservation laws,
Okay.
especially those with discontinuous fluxes like the one we're dealing with here.
Can you walk us through how this algorithm works?
Certainly. The core idea of front tracking is to approximate the smooth flux functions F and G with piecewise affine functions denoted by phi and G.
Okay.
Imagine replacing a smooth curve with a series of connected straight lines. That's essentially what we're doing here.
Oh, okay.
This simplification allows us to break down the problem into smaller, more manageable pieces.
So it's like a connect the dots version of the original flux functions.
Precisely.
Okay.
And this simplification is crucial because it allows us to solve these so-called Riemann problems,
Okay.
which arise at points where the initial data has a jump discontinuity.
Can you elaborate on these Riemann problems?
Sure.
What makes them so important?
A Riemann problem, in essence, is like having a sudden change in traffic density.
Okay.
Say, a sharp transition from free-flowing traffic to a complete standstill. Solving these Riemann problems is key to understanding how discontinuities in the solution evolve over time.
Okay.
In the context of this paper, the challenge is that the choice of which flux function to use phi or G
Depends on whether the jump is upward or downward.
so upward jump use phi, downward jump use G. Got it.
Yeah.
But earlier you mentioned sinks and sources appearing in the solution.
Right.
How do those fit into this front tracking picture?
That's where things get really interesting.
Okay.
The switching between F and G at local maxima and minima creates these sinks and sources,
Okay.
causing the solution's values to change over time.
Okay.
Equations 2.4 and 2.6 describe this dynamic.
Yeah.
F bar U is a local maximum.
Okay.
F bar U is a local minimum.
Okay.
It's like having a constant inflow or outflow of cars at certain points along the highway, even though there's no explicit source or sink term in the original equation.
So it's not just about approximating the smooth curves, but also accounting for these fluctuating densities caused by the switching flux.
Exactly.
Okay.
And this adds a layer of complexity to the front tracking algorithm.
It has to handle various scenarios like merging jumps,
Okay.
vanishing jumps,
Right.
and interactions between different fronts.
Right.
Each of these scenarios requires restarting the algorithm with updated initial data.
So it's a dynamic process,
Yes.
constantly adapting to the evolving solution.
Precisely.
Okay.
And what's particularly fascinating is that unlike in typical front tracking methods,
Yeah.
upward and downward jumps never cancel each other out in this model.
But why don't they cancel out? That seems counterintuitive.
The authors prove this in Lemma 2.1.
Okay.
They show that the shortest distance between points where the solution reaches a local maximum or minimum always stays positive.
Ooh.
In simpler terms, two opposing jumps, one upward, one downward, can approach each other, but they'll never completely collide and annihilate.
So it's like those jumps have a kind of repulsive force preventing them from fully merging.
That's a good way to visualize it.
Okay.
And this property is crucial for ensuring that the front tracking algorithm doesn't break down. It guarantees that we can always construct a well-defined, piecewise approximation of the solution.
Okay. So we have this connect the dots approximation that accounts for dynamic changes in density.
Right.
And avoids those mathematical collisions.
Correct.
What else do we need to know about the front tracking algorithm?
Well, there's one more crucial piece. Lemma 2.2.
Okay.
This lemma proves that the number of times you need to restart the front tracking algorithm
Okay.
due to those merging or vanishing jumps is finite.
And why is that important?
Because it guarantees that the algorithm will eventually terminate and produce a valid solution.
Okay.
Without this guarantee, the algorithm could potentially run forever,
Right.
constantly restarting and never converging to a final answer.
So Lemma 2.2 provides the safety net, ensuring that the algorithm doesn't get stuck in an infinite loop.
Exactly.
It's like having a guarantee that your GPS navigation will eventually get you to your destination.
That's a perfect analogy.
All right, so we've covered the front tracking algorithm and its key features.
Right.
What's next on our mathematical journey?
Now that we have a way to construct approximate solutions,
Right.
the next step is to understand their properties.
Hmm.
This is where section 3 comes in.
What kind of properties are we talking about here?
Sure.
What do we want to know about these approximate solutions?
The authors focus on establishing several key properties
Okay.
that are crucial for understanding the long-term behavior of these solutions.
Okay.
The first of these is outlined in Proposition 2.1.
Okay.
It states that certain quantities associated with the solution,
Okay.
namely the L1 norm, the total variation, and the L norm,
Right.
remain bounded as time progresses.
Can you break down what those norms represent
Yeah.
and why their boundedness is important?
Certainly. The L1 norm essentially measures the total mass of the solution,
Okay.
the total amount of stuff present. The total variation quantifies how much the solution oscillates,
Okay.
essentially capturing its spikiness. And the LU norm represents the maximum value the solution can attain.
Okay.
The fact that these norms remain bounded means that the solution doesn't blow up
Right.
or become uncontrollably wild as time goes on.
Okay.
It stays within certain limits,
Right.
which is a good sign for its stability.
So it's like saying the traffic jam, no matter how bad it gets, won't spread infinitely or have cars piling up sky high.
Exactly.
Okay.
These bounds provide a sense of control over the solution's behavior,
Right.
but perhaps the most crucial property.
Okay.
And this is where the stable case assumption really comes into play.
Yeah.
It's the comparison principle.
Intriguing. What does this comparison principle tell us?
The comparison principle, also stated in Proposition 2.1,
Right?
asserts that if you have two solutions to this conservation law,
Okay.
and one starts below the other,
Right.
it will stay below it for all time.
Okay.
Imagine two traffic jams,
Yep.
one initially worse than the other. The comparison principle ensures that the initially worse jam doesn't magically become better than the other as time goes on.
Hmm.
They maintain their relative order.
Okay, that makes intuitive sense.
Yeah.
But why is this comparison principle so important mathematically?
It's a cornerstone for proving many important results about the solutions.
Mm.
For instance, it allows us to prove that the L1 distance between two solutions,
Yeah.
a measure of how far apart they are,
Right.
never increases over time.
Okay.
This means that solutions don't drift apart from each other uncontrollably. They stay within a certain distance,
Okay.
which again hints at a form of stability.
So the comparison principle acts like a mathematical leash, keeping the solutions from running off in different directions.
Right.
It seems like this principle is key to showing that these front-tracking solutions converge to a unique limit.
You're absolutely right.
Okay.
The comparison principle, along with the boundedness of the norms,
Right.
lays the groundwork for proving the existence of a unique solution, which is the ultimate goal of the paper.
Right.
But before we get there,
Yeah.
we need to explore another important tool, vanishing viscosity approximations.
All right. That sounds like a whole other adventure. Before we jump into that, though, I think it's time for a quick recap.
Okay.
We've laid out the problem, a conservation law with a switching flux function, and explored the first tool for tackling it, the front tracking algorithm.
Right.
We've also seen some crucial properties of these approximate solutions, like the boundedness of the norms and the comparison principle.
Yes.
Now it's time to explore this new tool, the vanishing viscosity approximations.
Right.
Let's take a short break and we'll pick up the exploration in part 2 of this deep dive.
Sounds good. So we're ready to delve into the world of vanishing viscosity approximations.
All right, let's tackle this next piece of the puzzle. You mentioned that these vanishing viscosity approximations are another tool for understanding these conservation laws. Can you explain why we need a different tool? Doesn't the front tracking algorithm give us a pretty good handle on the solutions?
The front tracking algorithm is great for constructing approximate solutions and understanding their basic properties.
Okay.
But to prove the existence of a unique solution,
Right.
one that we can confidently say is the solution,
Okay.
we need a different approach. That's
Yeah.
where vanishing viscosity comes in.
So it's like we've built a model car, but now we need to make sure it drives like the real thing.
That's a great analogy. Vanishing viscosity approximations provide a way to connect our idealized model with its sharp jumps and piecewise affine functions
Right.
to a more realistic scenario where those sharp transitions are smoothed out. Think of it like adding a tiny bit of friction to our traffic flow model.
So instead of cars suddenly slamming on the brakes, we're allowing for more gradual slowdowns.
Exactly. And this smoothing effect is achieved by adding a small viscosity term to our original conservation law.
Okay.
Equation 1.6 in the paper shows how this modified equation looks. Epsilon plus epsilon, ucas, epsilon, uxon, uxlon.
Okay.
We've added this extra term on the right-hand side.
Okay.
Epsilon, uxlon, where epsilon represents a small positive number.
Okay.
This term acts like a mathematical friction, smoothing out any abrupt changes in the solution.
Okay. I see how this added term makes things smoother, but why is that helpful for proving the existence of a unique solution?
The beauty of adding this viscosity term is that it transforms our original equation into something called a uniformly parabolic equation.
Okay.
These types of equations are much nicer to work with mathematically.
Right.
They have well-established theories and techniques for proving the existence and uniqueness of solutions.
So it's like we're trading a bumpy dirt road for a smooth highway. We're making the mathematical terrain easier to navigate.
Exactly. And the key idea is that as we let this viscosity term epsilon shrink to zero,
Right.
the solutions to this smoothed out equation should converge to the solution of our original problem. It's like saying that as the friction becomes negligible, the behavior of our smoothed out model should approach the behavior of the original model with those sharp jumps.
So it's all about taking the limit as epsilon goes to zero and showing that everything converges nicely.
Precisely. But to do this rigorously, we need to carefully analyze the behavior of these viscous solutions.
Okay.
The solutions to the equation with the added viscosity term. That's what Section 5 is all about.
What are the key insights about these viscous solutions?
In Section 5, the authors focus on two specific families of viscous solutions that are crucial for their analysis: viscous shocks and near-constant solutions.
I remember we touched upon viscous shocks when discussing the front tracking algorithm.
Yeah.
Are they the same thing here?
Yes, they play a similar role. Remember how we approximated those sharp jumps in the solution with smoother curves?
Right.
Viscous shocks are those smoothed out versions of the abrupt transitions.
Okay.
They capture how the solution changes rapidly but continuously over a small region. Imagine a shock absorber in a car softening a sudden bump in the road that's analogous to what viscous shocks do in this mathematical setting.
So they make the mathematical ride smoother. What about these near constant solutions? What role do they play?
Near constant solutions capture the behavior of the solution near those local maxima and minima where the flux switching creates sources and sinks. Remember how the solution's value can change even though it's almost constant in those regions?
Right.
Near constant solutions allow us to analyze that subtle behavior.
Okay, so we have these viscous shocks handling the big jumps, and near constant solutions taking care of those subtle fluctuations near maxima and minima. Where do we go from there?
Section 6 is where the real magic happens.
Okay.
The authors take these two families of viscous solutions, the viscous shocks and the near constant solutions, and cleverly piece them together to construct an approximate solution that mimics the front tracking solution.
Okay.
It's like building a model car that perfectly replicates the movements of a real car, even though it's made of different parts.
So they're combining the best of both worlds.
Right.
They're using these well-behaved viscous solutions to create an approximation that captures all the essential features of the front tracking solution.
Exactly. And this is a brilliant move because it allows them to leverage the powerful tools of parabolic PDE theory to analyze this approximation.
But how do we know that this Frankensteinian creation, this piecing together of different solutions, actually works?
Yeah.
How do we know it's a good approximation?
That's where Section 7 comes in. This section is all about proving error estimates.
Okay.
The authors rigorously demonstrate how close their approximation is to the true solution. They quantify the accuracy of their construction, showing that the pieces fit together incredibly well.
So they're not just saying, hey, this looks pretty close. They're backing it up with solid mathematical proof.
Absolutely. It's like they're giving us a guarantee on the accuracy of their model car.
Okay.
They're saying, look, the difference between how this model car behaves and how a real car behaves is incredibly small, and we can prove it.
That's some impressive mathematical craftsmanship. I'm starting to see how all these pieces, the front tracking, the vanishing viscosity, the error estimates, fit together to build a solid foundation for proving the existence of a unique solution.
You're getting it. The authors have laid out a very intricate and elegant argument.
Before we move on to the final stages of their proof, can you quickly recap the key takeaways from the vanishing viscosity approach?
Certainly. The key idea is to smooth out the original problem by adding a small viscosity term.
Right.
This allows us to tap into the well-established theory of parabolic equations.
Okay.
By carefully analyzing the behavior of these viscous solutions and constructing a clever approximation,
Right.
we can then show that as the viscosity vanishes,
Ah.
we recover a solution that closely matches the one obtained through front tracking.
Okay.
This provides strong evidence that we're on the right track to proving the existence and uniqueness of a solution.
All right. I feel like we've gained a good understanding of the vanishing viscosity approach and how it connects to the front tracking method. What's the next step in this mathematical journey?
Now that we have these two powerful tools, front tracking and vanishing viscosity, the authors can finally start piecing together the final stages of their proof.
Okay.
They need to demonstrate that these approximations converge to a unique limit which represents the true solution to the original problem.
Okay. Sounds like we're heading into the grand finale. Let's dive into those final stages in part 3 of this deep dive.
I'm ready when you are.
So we're back and ready to tackle these final stages of this proof. We've explored the front tracking algorithm, delved into vanishing viscosity approximations, and now it's time to see how it all comes together. Where do we go from here?
The authors now need to show that all these approximations, these different ways of looking at the problem, actually converge to the same unique solution. It's like having multiple maps leading to the same destination. We need to prove that they all converge to the same point.
All right, we need to make sure we're not ending up in different mathematical cities. How do they go about proving this convergence?
They begin by focusing on how well those vanishing viscosity approximations actually satisfy the original conservation law. Remember, those approximations were solutions to a slightly modified equation with that added viscosity term.
Right.
Now we need to quantify how much they deviate from being true solutions to the original equation.
So it's like measuring the imperfections in our model car compared to a real one.
Yeah,
We need to see how much our approximation wobbles off course.
precisely. The authors introduce a quantity called E,
Okay.
which represents this error, how much the approximation denoted as WE fails to satisfy the original conservation law.
Right.
They then analyze how this error behaves as the viscosity parameter epsilon goes to 0.
Okay, so we're tracking this error as we make our approximation smoother and smoother. What are the key insights from this analysis?
The error analysis gets quite technical, but the key takeaway is that the error can be broken down into different components, each associated with a specific region of the solution. Remember, we have those regions around the local maxima and minima, the regions around the big jumps, and then those smoother regions in between.
It's a divide and conquer strategy. Tackle the error in each region separately and then add it all up.
Exactly. Let's start with those regions around the local maxima and minima. Remember, the solution is nearly constant there, but it changes over time due to those sources and sinks.
Right.
The key here is to show that the rate of change in our approximation closely matches the rate predicted by the front tracking solution.
So we want those near constant solutions to evolve in the same way, whether we're using the front tracking method or the vanishing viscosity method.
Precisely. And the authors achieve this by carefully choosing the parameters in their approximation, like the width of the intervals around those maxima and minima.
Okay.
They show that by making those intervals sufficiently small, the error in these regions can be made arbitrarily small.
Okay, so it's about fine-tuning the approximation to minimize discrepancies in those tricky regions.
Yeah.
What about those big jumps, the ones we handle with viscous shocks? They seem a lot harder to control.
You're right. Those jumps require a different approach. For the big jumps, we need to show that as we decrease the viscosity, those viscous shock profiles converge to the sharp jumps predicted by the front tracking solution.
Right.
Essentially, we need to make sure that our shock absorbers don't make the ride too smooth. We still need to capture those sudden changes in density.
So you want to strike that balance smooth enough to use the nice properties of parabolic equations, but not so smooth that we lose those essential features.
Exactly. The authors carefully analyze the properties of those viscous shock profiles, proving that they behave as expected and converge nicely to those sharp jumps as the viscosity vanishes.
That's reassuring. What about those smoother regions in between the jumps? Those seem less problematic.
You're right, the smoother regions are comparatively easier to handle. In those areas, the authors show that the vanishing viscosity approximation closely matches a mollified version of the front tracking solution. That's the one we get by smoothing out those small jumps that arise in the front tracking construction.
So in those calm regions, the approximation behaves nicely closely following the smoothed out front tracking solution.
Precisely. Now the final step is to put it all together.
Okay.
By combining the error estimates from each of those regions, the maxima, the big jumps, and the smoother regions, the authors demonstrate that the overall error can be made arbitrarily small.
So it's like saying that the wobbles in our model car can be made as tiny as we want, making its behavior almost indistinguishable from a real car.
That's a great way to put it. And this is the crux of their argument. They've shown that by choosing a sufficiently small viscosity and a sufficiently fine grid in the front tracking approximation, the difference between the two approaches becomes negligible.
So we have these two seemingly different methods converging to the same answer. That's a pretty powerful statement.
It is, and this convergence is the key to proving the existence of a unique solution.
Right.
Since both methods converge to the same limit, we can confidently say that this limit represents the solution to our original conservation law, the one with that switching flux function.
It's like those two maps leading to the same city, confirming that the city actually exists.
Exactly. And not only have they shown that the solution exists,
That's right.
but they've also shown that it's unique. There's only one city that satisfies all the conditions, all the rules laid out by our conservation law.
This has been an incredible journey, expert speaker. We started with this seemingly simple idea of a conservation law with a switching flux function, and it's led us through this intricate landscape of mathematical tools and techniques.
It's been a pleasure to guide you through it. This paper is a testament to the power of mathematical reasoning and the beauty of how different ideas can come together to solve complex problems.
I have to say I'm in awe of the level of detail and rigor the authors have put into this work. It's truly a masterpiece of mathematical analysis.
I completely agree.
Well, I think we've reached the end of our deep dive. We've unpacked the key findings, explored the mathematical machinery, and hopefully our listener now has a deeper understanding of this fascinating area of research.
I'd say we've accomplished our mission.
Before we wrap up, any final thoughts for our listener? Something to ponder as they continue their exploration of conservation laws.
I'd encourage your listener to think about the broader implications of this work. This paper focuses on a specific type of conservation law, but the ideas and techniques developed here can be applied to a wide range of problems in mathematics and physics. It's a reminder that even seemingly esoteric mathematical results can have far-reaching consequences.
That's a great point. It's a reminder that the world of mathematics is full of hidden connections waiting to be discovered. Thank you, expert speaker, for your insightful guidance. It's been a truly enlightening journey.
The pleasure was all mine.
And to our listener, we hope this deep dive has sparked your curiosity and equipped you with a newfound appreciation for the beauty and power of mathematics. Keep exploring, keep questioning, and keep diving deep. Welcome back, everyone, for another deep dive. This time, we're going to be tackling a paper called Conservation Laws with Discontinuous Gradient-Dependent Flux, the stable case.
Sounds good.
So buckle up, because this one is definitely a deep dive
for sure
into the mathematical trenches on this one.
I'm ready.
As always, I'm joined by our wonderful expert.
Happy to be here.
To help guide us through this.
Okay.
So
this paper is a fascinating exploration of a very unique type of conservation law. Instead of the usual flux function, depending solely on the conserved quantity, here it also hinges on whether the quantity's gradient is positive or negative.
So it's not just about how much stuff you have, but also like which direction it's moving.
Exactly. Think of it like traffic flow. The way cars behave.
When they're accelerating is different from when they're breaking even with the same traffic density.
Okay. Yeah, I can see that now.
Yeah.
You know, our listeners are math enthusiasts. So let's jump into the nitty-gritty of this paper.
Okay.
What's the overall structure?
So the authors use a combination of front tracking algorithms and vanishing viscosity approximations to analyze the solutions to this unusual type of conservation law. And they focus specifically on the stable case, which we'll unpack in detail.
Sounds intriguing. So what's on the first page?
So right off the bat, the authors introduced the main equation, equation 1.1, which describes the conservation law with this unusual flux function. The step function in 1.2 dictates which flux function, FU or GU, comes into play based on the sign of the solution's gradient.
So if the solution is increasing, we use G.
Precise.
And if it's decreasing, we use G.
Exactly. And they focus on the stable case, where FU is always less than G.
Why is this case called stable? So what makes it different?
In the stable case, the conservation law acts like a sink at local maxima and a source at local minima. So think about it. At a maximum, the solution is decreasing on both sides. So the smaller flux dominates, leading to a decrease in the overall value. Conversely, at a minimum, the solution's increasing on both sides. So the larger flux, GU, dominates, causing an increase. And figure 1 on page 1 illustrates this behavior beautifully.
So it's like the system is trying to smooth itself out over time.
Exactly. But this discontinuous flux function
introduces challenges in analyzing the solutions. So the authors introduce a smooth function in equation 1.3. And its properties in 1.4 to approximate the step function. This leads to the parabolic approximation, 1.6, which incorporates a viscosity term to address the discontinuity.
So they're adding a bit of smoothing to make the problem more tractable.
Exactly. And they make a key assumption about the flux functions. Assumption A1, which states that the difference between G and F must always be positive.
Why is this assumption important?
So it ensures that the smoothing effect of the viscosity term doesn't lead to unphysical behavior. Remember, the viscosity term is trying to mimic the switching between the two flux functions without this assumption. The approximation might smooth things out too much and lose that crucial switching behavior.
Oh, I see. So it's like a balancing act.
Exactly.
Between smoothing and preserving the essential features of the problem.
Exactly. And they also specify the initial condition in equation 1.8. Then comes the definition of a weak solution. Which is crucial because these conservation laws don't always have classical solutions.
Okay, remind me what a weak solution is again.
Sure. So a weak solution is a function that satisfies the conservation law in a weaker sense, allowing for discontinuities. So instead of requiring the equation to hold pointwise, we require it to hold in an integral sense when integrated against a smooth test function. Definition 1.1 on page 1 lays out the precise requirements.
It looks pretty technical.
Yeah.
What are the key takeaways?
The key points are that a weak solution must be continuous in L1 lock, meaning its integral over any bounded interval is finite. It must also satisfy equation 1.10 for all smooth test functions with compact support. This equation essentially captures the conservation law in an integrated form.
I think I'm starting to get the gist of it.
Great. And for simplification, they focus on spatially periodic solutions, which is a common approach in these types of analyses. Then they state theorem 1.1, which is the main result of the paper.
What does theorem 1.1 tell us?
So it asserts the existence of a contractive semigroup of solutions in L1 per LO. In simpler terms, it guarantees that for any initial data in this periodic setting, we can evolve the solution forward in time and get a unique solution that doesn't blow up in terms of its variation. It essentially says that the solution is well-behaved and doesn't become arbitrarily wild over time.
That's a powerful result.
Exactly.
It gives us a sense of predictability for these solutions.
Exactly. And the rest of the paper is dedicated to proving this theorem using the front tracking and vanishing viscosity approaches.
I'm eager to dive into those proofs. What's next on page 2?
On page 2, they start laying the groundwork for proving theorem 1.1 using front tracking. So it's a clever technique where you approximate the solution with piecewise constant functions. Essentially building it up from a series of fronts or jumps.
So instead of dealing with like a smooth, continuous solution, we're breaking it down into simpler building blocks.
Exactly. And the beauty of front tracking is that it allows you to analyze the evolution of these jumps quite explicitly. They replace the smooth flux functions f and g with piecewise fine approximations denoted by fan gaining in equations 2.1.
Why do they need to approximate the flux functions as well?
So it makes the analysis of the Riemann problems much easier. Remember, a Riemann problem is a fundamental building block in the theory of conservation laws. It involves solving the equation with piecewise constant initial data separated by a single jump.
And with piecewise affine flux functions. The solution to the Riemann problem is also piecewise constant.
Precisely.
Which simplifies things considerably.
Exactly. And they carefully lay out how to solve these Riemann problems using either Fan or Guy, depending on whether the jump in the approximate solution is positive or negative. But here's the interesting part. They handle intervals where the solution attains a local maximum or minimum differently.
Because that's where the flux function switches.
Exactly.
Between Pham and Guy. Leading to that source or sink behavior.
Precisely.
We talked about earlier.
Exactly. Instead of remaining constant on these intervals, the solution changes according to the ODEs in equations 2.4 and 2.6. Influenced by the difference between the two flux functions.
So the local maxima and minima are not static points. But rather they evolve over time, driven by this interplay between the two fluxes.
And this evolution affects the speeds of the jumps at the endpoints of these intervals, as shown in equations 2.5 and 2.7. The authors then list the scenarios that trigger a restart of the front tracking algorithm.
What do you mean by restart?
Well, as the front tracking solution evolves, several things can happen. Local maxima and minima can merge or cancel out, jumps can vanish. Or the Liu admissibility condition, which ensures the stability of the solution, can be violated in each of these cases. The algorithm needs to be restarted with updated initial data.
So it's not a one-shot process, but rather an iterative procedure
Exactly.
where you keep refining the approximation
Yeah.
as the solution evolves.
Exactly.
Oh.
And they highlight how the algorithm can be seamlessly restarted
Mm-hmm.
in each of these scenarios,
Okay.
ensuring that the construction of the approximate solution continues
Yeah.
without hiccups.
Right.
One crucial observation they make
Okay.
is that upward and downward jumps
Okay.
never cancel each other out,
Okay.
unlike in standard front tracking scenarios,
Why is that?
because of the unique behavior
Okay.
of this conservation law.
Mm-hmm.
The rate at which local maxima decrease and
Yeah.
minima increase
Yeah.
becomes infinitely large
Okay.
as the interval shrinks,
Mm.
ensuring that a jump vanishes before the interval collapses.
The system prevents those jumps from
Yeah.
getting too close
Yeah.
and annihilating each other.
Precisely.
Okay.
Lemma 2.1 formalizes this observation,
Okay.
establishing that the minimum length
Mm.
of such intervals remains positive
Okay.
throughout the evolution.
So we have a guarantee
Yeah.
that the front tracking algorithm won't get stuck because of collapsing intervals.
Exactly.
Okay.
Then comes Lemma 2.2,
Okay.
which demonstrates that the total number of restarts
Mm-hmm.
required in the algorithm is finite.
Okay.
This is crucial
Yeah.
because it ensures that the algorithm will eventually terminate
Right.
and produce a well-defined approximate solution.
That's reassuring.
Indeed.
We don't want to be stuck
Yeah,
in an infinite loop of restarts.
exactly.
And then Proposition 2.1
Yeah.
dives into some
Yes.
key properties of these front tracking solutions.
All right.
These properties are crucial for understanding the
Right.
long-term behavior
Exactly.
of the solutions.
Yeah.
And for connecting them to
Yeah,
the viscous approximations later on.
exactly.
Okay.
So,
Hit me with the highlights.
right.
What are the key takeaways?
So first, it establishes that the L1 norm
Okay.
of the approximate solution
Mm-hmm.
doesn't increase over time.
Okay.
This means that the total mass
Mhm.
of the solution
Yeah.
is either conserved or decreases,
Right.
which makes sense for a conservation law.
It's like saying the total amount of stuff in
Yeah,
this system can't magically increase out of nowhere.
exactly.
Yeah, okay.
Second,
Yeah.
it shows that the total variation
Okay.
and the L norm of the solution also don't increase.
Okay.
The total variation measures
Yeah.
how much the solution oscillates,
Okay.
while the L norm measures its maximum value.
So these results tell us that the solution doesn't become
Yeah.
wilder or more extreme
Ex-
as time progresses.
It either stays the same
Okay.
or smooths out.
Okay.
Third, it establishes a comparison principle,
Right.
which is a fundamental property
Yeah.
in the theory of PDEs.
Okay.
It essentially says that
Right.
if one initial condition
Okay.
is always less than or equal to another,
Hmm.
the corresponding solutions
Okay.
maintain that ordering for all times.
Okay. That makes intuitive sense.
Exactly.
If you start with less stuff,
Yeah.
you can't end up with more stuff
Exactly.
than someone who started with more.
Exactly.
Yeah.
And finally, we have the contraction property,
Okay.
which is a crucial ingredient for
Yeah.
proving the existence of a semigroup.
Okay.
It states that the L1 distance between two solutions
Yeah.
doesn't increase over time.
So even if the solutions start out far apart, they can't drift further apart as time goes on.
Precisely.
Okay.
These properties are essential for understanding the
Yeah.
long-term behavior of the system.
Yeah.
And for connecting the front tracking solutions
Yeah.
to the viscous approximations later on.
Right.
They paved the way for defining a contractive semigroup S,
Okay.
as they do in equation 2.26.
Mm-hmm.
This semigroup captures the evolution of solutions,
Okay.
starting from any initial data in L1.
Right.
They then extend this
Oh.
to a limit semigroup S,
Mm.
obtained as AE goes to infinity.
So they're essentially showing
Yeah.
that these front tracking approximations, as they become increasingly refined,
Yeah.
converge to a unique solution
Exactly.
described by this limit semigroup S.
Exactly.
Okay, that's a powerful result.
It is.
And theorem 2.1
Yes.
formally establishes
Yeah.
the existence of this limit semigroup
Yeah.
and its contraction property.
Exactly.
This theorem lays the foundation for the connection
Yes.
between front tracking
Mm.
and vanishing viscosity.
It's ice.
Okay, so we've now laid the groundwork
Right.
for understanding the solutions
Yeah.
obtained through front tracking.
Yes.
But the story doesn't end there,
It does not.
does it?
No.
Now we need to connect these front tracking solutions
Right.
to the viscous approximations.
You're absolutely right.
Okay.
The paper then turns its attention to a deeper analysis of these viscous approximations.
Okay.
Let's delve into section 3.
Okay.
Which explores the properties of solutions obtained through this alternative approach.
Perfect. So let's see how these properties align with what we've learned so far.
Exactly.
Welcome back to our deep dive into conservation laws with discontinuous gradient-dependent flux, the stable case.
Okay.
Last time we left off with a bit of a cliffhanger.
Yeah.
The authors had shown that weak solutions, even with entropy conditions, might not be unique.
Right.
Raising the question of how to identify the physically relevant solution.
Exactly. And as we hinted at, the authors argue that the vanishing viscosity approach provides the key to resolving this ambiguity. Essentially, they show that the solutions to the viscous approximation as the viscosity goes to 0 converge to the same unique solution obtained through front tracking.
So it's like the viscosity acts as a guide.
Precisely.
Leading us to the correct solution. Among the potentially many weak solutions.
Exactly.
Okay.
And they achieve this through a remarkably intricate construction.
Okay.
They build a special approximate solution that bridges the gap between the front tracking and vanishing viscosity approaches.
Okay. I'm intrigued. Where does this construction begin?
So section 4 sets the stage.
Okay.
The authors introduce the parabolic equation 1.6, which incorporates the viscosity terms.
All right.
And they note that for any initial data in L1 per R, the Cauchy problem for this equation has a unique solution.
So adding viscosity ensures the existence of a well-behaved,
smooth solution. Exactly. Okay. And they emphasize that the comparison principle, which we discussed earlier, still holds in this viscous setting.
So if one initial condition is less than or equal to another, the corresponding viscous solutions maintain that ordering for all times.
Exactly. And by writing the viscous equation in conservation form, as in equation 4.2, they establish the contraction property, which is expressed in equation 4.3.
So this means that the L1 distance between two viscous solutions doesn't increase over time. Just like we saw with the front tracking solution.
Exactly. And this contraction property implies that the total variation of a viscous solution with bounded initial variation also doesn't increase over time.
So again, we see the theme of well-behaved solutions.
Precisely.
They don't become wilder or more oscillatory as time progresses.
And these properties pave the way for Theorem 4.1, the central result of this section.
Okay, what does Theorem 4.1 tell us?
This theorem asserts that as the viscosity terms vanish and go to 0, the viscous solutions converge to a unique limit. And that limit is precisely the same solution obtained through front tracking.
That's a remarkable result.
It is.
It bridges the gap between these two seemingly distinct approaches.
Exact.
Showing that they ultimately lead to the same solution.
Precisely.
Okay, but how do they actually prove this convergence? It sounds like a very technical challenge.
The heart of the proof lies in the construction of a special approximate solution denoted by W, which carefully mimics both the front tracking solution and the viscous solution.
All right. And so Proposition 4.1 outlines
the key properties.
Okay, that this W must satisfy.
Okay, let's break down Proposition 4.1.
All right.
What are the key requirements for this W?
So first, W needs to be close to the front tracking solution. In the L1 sense, as expressed in equation 4.6, essentially for a given tolerance, we want to ensure that the integral, or the absolute difference between W and U, is less than 0.
So we're saying that W needs to approximate the front tracking solution to within a certain error.
Second, W must be sufficiently smooth with C11 regularity, except at a finite number of points where it's allowed to have jumps.
So it can't be too jagged or rough.
Precisely. Equation 4.7 then quantifies how closely W satisfies the viscous equation, allowing for a small error
integrated over time and space.
So it doesn't have to be
Yeah.
a perfect solution to the viscous equation,
Right.
but it needs to come pretty close.
Exactly.
All
And
right.
finally,
Yeah.
condition 3
Mm-hmm.
in proposition 4.1
Okay.
limits the total sum of the jumps in W
Okay.
at those discontinuity points.
So the jumps can't be
Yeah.
too large or too numerous.
Precisely.
Okay.
Constructing this W
Yeah.
is no easy feat.
Right.
It's like walking a tightrope,
Yeah.
balancing smoothness,
Mm-hmm.
closeness to the front tracking solution,
Right.
and approximate satisfaction
Yeah.
of the viscous equation.
Sounds like a mathematical juggling act.
Yeah.
How do they pull it off?
Sections 5 and 6
Okay.
are dedicated to this intricate construction.
Right.
The authors introduce
Yeah.
2 special families of viscous solutions
Mm-hmm.
that serve as the building blocks for W.
Okay.
The first family focuses on viscous shocks,
Okay.
which are smooth traveling wave solutions to the viscous conservation law.
So they're essentially smoothing out
Exactly.
those sharp,
Yeah,
discontinuous jumps
Right.
that we had in the front tracking solution.
exactly.
Okay.
They carefully analyze
Yeah.
the properties of these viscous shocks,
Okay.
ensuring they satisfy
Mhm.
the Lou admissibility condition.
Right.
And they introduce a clever modification
Okay.
to the flux functions F and G
Mhm.
to make the analysis more tractable.
Okay. And what about the second family?
So the second family
Yeah.
focuses on solutions
Yeah.
that approximate the behavior of the front tracking solution
Yeah.
near local maxima and minima.
Right. Because that's where we have
Exactly.
that interesting source or sink behavior
Right.
due to the switching flux.
Exactly.
Right.
So they need to find viscous solutions
Yeah.
that mimic this switching behavior. And they do this through a clever construction involving an auxiliary function Z, which allows them to build viscous solutions that capture the dynamics near those critical points.
Okay, so now they have these 2 special families
Okay.
of viscous solutions,
Yeah.
smoothed out shocks,
Mhm.
and functions that capture the behavior
Yeah.
near local maxima and minima.
Exactly.
What do they do with them?
Section 6
Okay.
outlines the meticulous process
Okay.
of piecing these building blocks together
Mm-hmm.
to create the approximate solution.
Okay.
They divide the time interval
Yeah.
into subintervals,
Okay.
where the front tracking solution
Mhm.
has a constant structure,
Okay.
meaning the number and sizes of the jumps
Okay.
remain above a certain threshold
Right.
within each subinterval.
Yeah.
They construct
The crown.
3 types of approximate solutions
Okay.
on overlapping domains.
Okay, tell me about these 3 types.
So type 1 solutions
Yeah.
use the special functions that approximate the behavior
Yeah.
near local maxima and minima. Okay.
Placing them strategically
All right.
around those critical points.
Okay.
Type 2 solutions.
Yeah.
Employ the smoothed out viscous shock profiles
Okay.
to approximate the
Yeah.
large jumps
Mm-hmm.
in the front tracking solution.
Okay.
And type 3 solutions
Yeah.
cover the remaining intervals,
Okay.
where the front tracking solution is monotone
Mm-hmm.
but doesn't have large jumps.
Okay.
They achieve this by using a technique
Yeah.
called mollification,
Okay.
which essentially smooths out
Okay.
the front tracking solution in those regions.
So it's like they're taking a mosaic approach,
Exactly.
using different types of tiles
Yeah.
to create a smooth,
Yeah.
continuous approximation
Yeah.
of the front tracking solution.
Exactly.
Okay.
But the challenge doesn't end there.
Right.
They then need to glue these
Yeah.
different types of solutions together
Okay.
seamlessly,
Right.
ensuring that the values and derivatives match
Mm-hmm.
at the junctions. That sounds like a delicate operation.
It is.
Okay.
They achieve this through a series of clever steps
Okay.
involving auxiliary functions
Mhm.
and modifications to ensure
Sure.
smoothness and periodicity. The details are quite technical,
Okay.
but the key takeaway is that they managed to construct
Yeah.
this women
Okay.
that satisfies all the requirements of
Oh.
Proposition 4.1.
So they've shown that this carefully crafted WUMA
Yeah.
is both close to the front tracking solution
Mm-hmm.
and nearly satisfies the viscous equation.
Exactly.
What's the final step?
So Section 7
Okay.
is devoted to proving that this WUMA,
Yeah.
with all its intricate properties,
Mm-hmm.
actually implies the convergence
Okay.
of the viscous solutions
Yeah.
to the same semigroup obtained through front tracking.
All right.
They carefully analyze the error terms,
Okay.
leveraging the properties
Mhm.
of the viscous shock profiles,
Okay.
the special functions near critical points,
Mm.
and the mollifications, and they show that as the viscosity goes to 0,
Okay.
these error terms vanish,
Yeah.
leading to the desired convergence.
Wow, that's impressive.
Yeah,
They've really pulled out all the stops
they have.
to prove this result.
And with that,
Yeah.
they've achieved the main goal of the paper,
Good.
showing that the front tracking and vanishing viscosity approaches,
Yeah.
despite their differences,
Yeah.
ultimately lead to the same unique solution
Wow.
for this intriguing type of conservation law.
This deep dive has been a whirlwind tour
It has.
of advanced mathematical techniques.
It's a testament.
We've encountered front tracking,
Just the power
vanishing viscosity,
and beauty
Riemann problem,
of mathematics.
entropy conditions,
Yeah.
mollification,
And it highlights a whole lot
of intricate analysis.
and ingenuity required.
I have to admit, I'm feeling a bit exhausted
Yeah.
after all that,
I do.
but in a good way.
In a good way.
It's been an incredibly stimulating journey,
Yes, it has.
and I've learned a lot
Yeah.
about this fascinating area of mathematics.
It is a fascinating area.
A huge thank you
Well, thank you for having me.
to expert speaker for expertly guiding us through
Oh, of course.
this mathematical labyrinth.
Happy to be here.
And to you, dear listener,
Yeah.
thank you for joining us on this deep dive.
Thanks for listening.
We hope you've enjoyed the journey
Yeah.
as much as we have.
It's been a pleasure.
Until next time, keep those mathematical minds
Absolutely.
curious and engaged,
Keep diving deep.
and keep diving deep. All right, so we're diving into this paper today. It's called Conservation Laws with Discontinuous Gradient Dependent Flux, the stable case. Yeah, quite a mouthful. But the idea is actually pretty cool. It's like, you know those conservation laws? Well, imagine if the way things flow, like the flux function, changes depending on whether, the solution is increasing or decreasing.
Yeah. It's a bit like you could imagine a traffic flow model, right? Where the cars accelerate differently going downhill than uphill.
Exactly.
Yeah.
And that difference in acceleration would lead to different kind of flux, you could say, depending on, well, the slope. So this paper, it really jumps right in, setting up the problem with equation 1.1 on page 1. And they've got this conservation law, but the flux function it's like a combination of two functions, fu and gu, and then there's this step function that determines which one is active at any given point.
Right. So that step function, it's denoted by hex, and it basically acts as a switch. Like, depending on whether the solution's gradient, that's US, is positive, meaning the solution's increasing, or negative, meaning it's decreasing, it flips between FU and GU.
Okay, so it's like it's constantly checking which way the solution is trending, up or down, and then adjusting the flux accordingly. And for this particular paper, they're focusing on the stable case, which means that F is less than GU. So the flux is lower when the solution is increasing.
Exactly. Think of it like the traffic analogy again. If you're going uphill, the density of cars is increasing, the flux is lower because everyone's braking. But going downhill, density decreases, cars can speed up, so the flux is higher. And this creates like almost a source at the bottom of the hill and a sink at the top.
I see. So it's like the very shape of the solution, the fact that it's increasing or decreasing, is influencing the way things flow. That's pretty wild. But I imagine dealing with that step function directly would be a mathematical nightmare, wouldn't it? It's so abrupt, so discontinuous. How do they even start to analyze this?
Yeah, good point. It'd be pretty tricky to work with directly. So they introduce this really clever workaround, and they explain it on pages 1 and 2. It's called a parabolic approximation, and it's given by equation 1.6. Basically, instead of that harsh step function, they use a smooth function. It's denoted by the of x, and it approximates the step function, but with a gradual transition. And this transition is controlled by a parameter, ax.
So they're essentially smoothing out that sudden jump, making it more like a gentle curve. But, this is still just an approximation, right? How do we know that it actually reflects what's going on in the original problem?
That's a great question. And that's where the idea of weak solutions comes into play. On page 2, they give definition 1.1, and this definition spells out exactly what it means for a function to be considered a weak solution to this kind of conservation law.
Okay, I'm with you. But what makes a solution weak in this context? I mean, is it like it's not as good as a regular solution or something?
Not exactly. It's more like a weak solution might not be perfectly smooth. It might not be differentiable everywhere. But it still, in a way, satisfies the conservation law, just in a broader sense. So, definition 1.1 says that the solution has to be continuous in time. And it introduces this other function, a measurable function called lec, which is there to track the sign of the solution's gradient. But the really important part is this integral condition, equation 1.10. This condition makes sure that even with those jumps in the flux, the overall quantity being modeled is still conserved.
Yeah, that makes sense. It's like, even though there are these sudden changes happening, the overall flow, the balance, still has to be maintained. That's really interesting. Now, turning to page 3, they start talking about spatially periodic solutions and this function space, L1 per.
Yeah.
Can you explain what that's all about? Why that specific choice?
Sure. It's basically a way to make the math a bit more manageable without losing any of the essential information. Imagine you're, studying traffic on a circular track. What happens in one lap is going to repeat in the next, right? Well, spatially periodic solutions capture that idea, and L1 per R, that's just the space of functions that are periodic and integrable over one period.
Okay, so it's a simplification, but it still reflects the fundamental nature of the problem. It's like zooming in on a representative section and understand that the same pattern will continue.
Yeah.
And this leads us to the big review, right? Theorem 1.1, also on page 3.
Exactly. This theorem, it's a key result. It states that as you shrink that smoothing parameter and the viscosity parameter in their parabolic approximation, those solutions actually converge to a unique limit. And this limit, this is the crucial part, it's a weak solution to the original conservation law.
So it's like their approximation, it's not just some random guess, it's actually leading us to a real valid solution. But they also mention, and I found this really interesting, that this limit is the same whether you use front tracking or vanishing viscosity. What's the significance of that? Why is that important?
It's a good observation, and it suggests that this solution it's robust, It's not just an artifact of using one specific method. Front tracking, that focuses on how those sharp jumps in the solution evolve over time, while vanishing viscosity, that gradually smooths out the whole problem. So the fact that both of these approaches, even though they're quite different, lead to the same limit, that's pretty remarkable. It's like two explorers starting from different points and ending up at the same hidden treasure.
I love that analogy. So how do they go about proving this remarkable theorem? Page 4 gives a little peek into their strategy.
Right. They outline a multi-step approach. First, they're going to construct these things called front tracking approximations, then analyze their properties, and finally show that both the front tracking and the vanishing viscosity solutions converge to that same limit.
It sounds like a very meticulous construction project.
Yeah.
But there's also this remark 1.1 on page 4, and it hints at something a little bit unsettling.
Yeah, this remark raises a crucial point. It's like, okay, we've shown that front tracking and vanishing viscosity both lead to the same solution. That's great. But there's a chance that there are other weak solutions out there, solutions that we don't get from these methods. Like, we found one treasure chest, but there might be others hidden nearby.
That's a bit unnerving.
Uh-huh.
So just satisfying the definition of a weak solution, maybe that's not enough. We might need additional criteria, some way to be sure we found the right solution.
You're hitting on a really key point, and it's something the authors grapple with throughout the paper. It's like, how do we know we've found the genuine article, the solution that actually represents the true behavior of the system? That's one of the big challenges here.
Right. So how do they even begin to tackle this problem? How do they sift through those potentially many weak solutions and find the right one?
Well, they start by simplifying things a bit. On page 5, they explain how they approximate those smooth flux functions, F and G, with piecewise affine functions. These are denoted by affine G. Think of it like replacing a smooth curve with a series of straight lines. It's an approximation, but it captures the overall shape.
So it's a way to break the problem down into smaller, more manageable pieces. But how do they make sure that these straight lines, these piecewise functions, actually represent the original curves accurately?
They use a parameter to control the accuracy of the approximation. The idea is that these piecewise functions, they actually coincide with the original functions at specific points, and these points are determined by EF. So as you increase E, you get a finer and finer approximation. It's like, adding more detail to a drawing.
Ah, I see. It's like controlling the resolution of the image. The higher the resolution, the more accurately it reflects the original. Okay, so they're carefully approximating those smooth curves. But what about those jump points? Those places where the solution abruptly changes. How do they deal with those when they're using these piecewise functions?
That's another great question. They address it head on, actually, also on page 5.
Mm.
They talk about solving the Riemann problem at each of these jump points. And the choice of which flux function to use, either phi or g, it depends on whether the solution is increasing or decreasing at that particular jump.
So they're making sure that even at those sudden jumps, their approximation still respects the direction of change, whether things are going up or down. Okay, that makes sense. But things get even more complicated, don't they? I mean, what about those local maxima and minima, those peaks and valleys in the solution? How do they incorporate those into this front tracking approximation?
Yeah, you're absolutely right. It gets even trickier. And that's where they have to make some further adjustments. On pages 5 and 6, they introduce something called source turns into their front tracking approximation, specifically in equations 2.4 and 2.6. These source terms, they actually cause the solution's value to change over time. And that's different from the usual front tracking, where the values at those jumps usually stay constant.
So it's like those peaks and valleys, they're not just static features. They're constantly evolving, being shaped by those flux dynamics. It's almost like a landscape that's constantly shifting and changing. But with all this change happening, with those source terms constantly at work, how do they guarantee that this front tracking algorithm doesn't just go crazy? How do they keep it under control?
That's where their approach gets really clever, and it's a big part of what makes this paper so interesting. On pages 6 through 8, they detail all the different scenarios where the front tracking algorithm needs to be essentially restarted. They've got 3 main cases they talk about: merging or cancellation of those local maxima and minima, violation of the Lou admissibility condition because of those changing solution values, and the interaction of multiple fronts. And these restarts, they act like safety checks, you know?
Okay.
They keep the algorithm on track, making sure it's producing something meaningful.
It's like they're constantly monitoring the solution, making adjustments as needed to prevent it from spiraling out of control. But how do they actually prove that these front tracking approximations are even well-defined in the first place? How do they know it's not all just going to collapse at some point?
They lay out the groundwork for that on pages 8 and 9 with a couple of lemmas, lemma 2.1 and lemma 2.2. These lemmas provide the safeguards, so to speak. Lemma 2.1, it proves that the shortest length of those intervals where the solution has a local maximum or minimum, well, it always stays positive, so they can't just shrink down to a point and cause problems. And then, using that, lemma 2.2 shows that the algorithm only needs a limited number of those restarts, those corrections, and this leads to a solution that has a controlled number of jumps.
Okay, so it's not just about keeping the algorithm running. It's about ensuring that it produces a solution that's actually meaningful, something we can work with. But what about the behavior of these front tracking solutions? What kind of properties do they exhibit?
That's where we start to delve into some really interesting results. And it all begins with proposition 2.1 on pages 9 and 10. This proposition outlines some key characteristics of these front tracking solutions.
Okay, I'm all ears. What does proposition 2.1 tell us about these solutions? What makes them tick?
Well, it highlights 3 important properties. First, it establishes that the L1 norm of the solution, which basically measures its overall size, decreases over time. Second, it shows that the total variation, which quantifies how much the solution fluctuates up and down, also decreases over time. And finally, and this is crucial, it establishes what we call the comparison principle. This principle states that if one solution starts below another solution, it stays below it.
So there's a built-in stability to these solutions, right?
Yeah.
They're shrinking in size, they're becoming less wiggly, and they're maintaining their relative order. That's pretty remarkable. But I noticed that proposition 2.1, it only deals with piecewise constant initial data. What about more general initial data? Can their method handle those as well?
That's a sharp observation. And yes, the paper does address this in remark 2.1 on pages 11 and 12. They explain how the front tracking algorithm can be extended to handle arbitrary initial data in L1R through a clever limiting process. It's like approximating a curved line with a series of increasingly refined staircases.
That's a neat trick. So it's like, even if our starting point isn't perfectly aligned with their assumptions, we can still use their method by gradually refining our approximation. And this brings us to, I think, a pivotal moment in the paper, right? Theorem 2.1 on pages 12 and 13. This is where they finally prove that as E increases, those piecewise affine approximations, they actually converge to a unique limit. What's the significance of this result? Why is this theorem so important?
Theorem 2.1 is a cornerstone of their whole argument. It basically demonstrates that those piecewise affine approximations, they're not just arbitrary stepping stones. They're actually converging to something meaningful, a well-defined limit, which they denote as semigroup S. And this semigroup, this is our candidate. This is what we believe is the solution to the original problem.
So they've built a bridge, haven't they? They've connected those approximations to a proper solution. That's a huge accomplishment. But how confident can we be that these front-tracking solutions are actually close to the true solution? Is there any way to measure how accurate these approximations are?
Absolutely. That's a crucial question. And Proposition 2.2 on page 13 provides that assurance. It gives us what's called an error bound. This is a mathematical guarantee of how far the front tracking approximation is from the actual solution. And the amazing thing is this error, it decreases exponentially as it increases. So as we add more detail to those piecewise approximations, they get closer and closer to the true solution. And they do so very rapidly.
So it's not just converging, it's converging like at an incredible speed. That's very reassuring. Now, the paper then takes a bit of a turn and starts to explore some pretty surprising behavior of these solutions. Proposition 3.1 on pages 14 and 15 reveals a rather unexpected result. These solutions, they eventually decay to zero in a finite time. And what's even more surprising is that this happens even without imposing some of those typical assumptions, like genuine nonlinearity of the flux functions. This kind of decay, it's not something you usually see in typical conservation laws, is it? Why is that? What's going on here?
That's a great question, and it really gets to the heart of what makes these conservation laws with discontinuous flux so unique. This unusual behavior, it stems from the interplay between those two flux functions, F and GU. That constant switching back and forth, governed by the solution's gradient, it creates a kind of damping effect. And this effect ultimately drives the solution down to zero.
Ah, I see. So it's like the very nature of the discontinuous flux, it's like a built-in self-destruction mechanism for the solution.
Yeah.
But we've also been talking about properties like bounded variation and the semigroup structure of these solutions. Do these play a role in this decay to zero, or are they just interesting side notes?
No, those properties are actually crucial for understanding this behavior. Propositions 3.2 and 3.3, discussed on pages 15 and 16, they highlight these connections. Proposition 3.2, it establishes that the limit solution has bounded variation, meaning it doesn't fluctuate too wildly. This well-behaved nature is a key factor in its long-term behavior. And then Proposition 3.3, it confirms that this limit solution, the one we get from front tracking, actually satisfies the definition of a weak solution. So it's not just some mathematical phantom, it actually follows the rules of the game.
That's a relief. But then we encountered example 3.1 on pages 17 and 18, and this example throws a bit of a wrench into the works, doesn't it?
Yeah.
What's the point of this example? Why did the authors include it?
Example 3.1 it's like a cautionary tale. It demonstrates that just because a solution is weak, it doesn't necessarily mean it's unique. It shows that there can be multiple weak solutions, and some of them, well, they might not reflect the true behavior of the system. This example actually constructs a solution that fits the definition of a weak solution perfectly, but it doesn't match up with the one we get from front tracking or vanishing viscosity.
So it's like we found a counterfeit treasure chest. It looks like the real deal, but it doesn't actually contain the true treasure. And this brings us back to that question we were talking about earlier.
Yeah.
How do we tell the difference between the genuine solutions and these imposters?
That's the million-dollar question. And example 3.1, it really underscores the need for something more. We need more refined criteria, something beyond just satisfying the basic definition of a weak solution to help us identify the physically meaningful solutions and weed out those misleading ones.
Right. So simply being a weak solution isn't enough. We need something more, something that captures the essence of those smoothing methods that led us to the right solution in the first place.
Exactly. And finding those additional criteria, those admissibility conditions, that's one of the big open questions in this field. It's a challenge that the authors acknowledge and invite further research to explore.
So it's a journey that's still ongoing. We've made some incredible progress, but there's still much to discover.
Absolutely. And that's what makes this area of research so exciting. There's still so much to learn and understand about these fascinating equations.
Yeah, so those properties, those are really important, and they're not just interesting side notes. They actually give us valuable insight into the long-term behavior of these solutions. And also, they support the idea that using those smoothing methods like front tracking and vanishing viscosity, that's actually a valid approach.
Okay, so those properties they're not just there for show, they actually have some real substance. Exactly. And we see this in propositions 3.2 and 3.3, which are discussed on, let me see, pages 15 and 16. They highlight these connections really nicely. Proposition 3.2, it establishes that the limit solution, the one we're interested in, it has bounded variation.
So it doesn't like fluctuate too
Wildly.
wildly.
Exactly. It's well behaved. And that's really important for understanding how it behaves in the long run.
Right. So it has some kind of inherent stability. That's good to know.
Yeah. And then proposition 3.3, this one, it confirms that this limit solution, the one we get from front tracking, it actually satisfies the definition of a weak solution.
So it's not just a mathematical phantom. It actually fits the bill, so to speak.
Right, exactly. It actually plays by the rules. But then we come to example 3.1, and this is on pages 17 and 18.
Yeah, example 3.1. This one's a bit of a head scratcher, isn't it?
It is. It kind of throws a wrench into things, you know. It demonstrates that just because a solution is weak, it doesn't necessarily mean it's unique.
Wait, so there could be like multiple weak solutions, but
Right.
wouldn't that mean that some of them might not be the real solution, the one that actually reflects what's happening?
That's exactly the point. And this example 3.1, it actually constructs a solution that's a perfectly valid weak solution, but it doesn't match the one that we get from front tracking or vanishing viscosity.
So it's like we've been following this path, we think we found the treasure, but then it turns out it's a fake, it's a decoy.
Yeah, it's a good analogy. And this example, it really underscores the need for something more, you know. We need more than just the basic definition of a weak solution.
We need some way to filter out those fake solutions, those imposters.
Exactly. We need some additional criteria, some way to be sure that we found the genuine article, the solution that actually represents the true behavior of the system.
Right. So simply being a weak solution, that's not enough. We need something stronger, something that really captures the essence of what's going on.
Absolutely. And that's a big open question in this field. And, you know, the authors, they acknowledge this. They basically say, hey, this is something that needs more research. We need to figure out what those extra conditions are, those admissibility conditions.
So it's a challenge for future mathematicians, right? To figure out how to separate the wheat from the chaff, so to speak.
Exactly. But before we dive into that too deeply, the paper introduces another element, which they call viscous approximations. This is on, let's see, pages 18 and 19.
Okay, viscous approximations. What are those all about?
Well, they're kind of like, you know, remember how we talked about using that sand analogy to smooth things out? Well, viscous approximations are kind of like reintroducing that sand. They involve adding a small viscosity term to the equation, which makes it parabolic. And this is shown in equation 4.2. And this smoothing, it makes the equation what we call well-posed, which means it has a unique and stable solution.
So it's like we're taking a detour through smoother terrain to get a better understanding of the rough landscape.
Yeah, that's a good way to put it. But the question then becomes, how do these viscous approximations, how do they relate to the front tracking solutions we've been talking about?
Right. Are they totally separate approaches, or is there some connection between them?
And that's where theorem 4.1 comes in. This is stated on page 19. And this theorem, it's pretty amazing. It states that as that smoothing parameter and that viscosity parameter, as they approach zero, the solutions that we get from these viscous approximations, they actually converge to the same semigroup solution that we got from front tracking.
Wow. So it's like those two explorers, the ones we were talking about earlier, they finally meet up and they realize they were both on the right track all along.
Exactly. And it's a really powerful result. But proving it, well, that's no walk in the park.
Yeah, I bet. So how do they even approach something like that?
Well, the key to proving it lies in proposition 4.1. And this is discussed on pages 19 and 20. This proposition, it aims to show that any front tracking solution, any one you can think of, can be closely approximated by a solution to the viscous equation.
So it's like we can mimic the behavior of the front tracking solution using a carefully chosen viscous solution.
Precisely. And to do this, they construct a special approximate solution, and they denote this by W. And this W, it acts like a bridge between the front tracking and the viscous solutions. It's like it can speak both languages, so to speak.
So W is like a translator, helping these two different approaches communicate with each other. That's pretty neat. But what is it about W that makes it so special? What are the key characteristics that allow it to play this bridging role?
It has to satisfy three main properties. First, it has to closely resemble the front tracking solution, and this is expressed mathematically in equation 4.6. Second, it has to be piecewise smooth, which means it's smooth within certain intervals, but it can have controlled jumps at specific times. And this is outlined in equations 4.7 and 4.8. And essentially, they create this hybrid solution that captures the essence of both front tracking and viscous approximations.
So it's like a chameleon. You can adapt to both the sharp, discontinuous world of front tracking and the smooth, continuous world of viscous approximations.
Exactly. But constructing this hybrid solution, it's a very delicate process. It's not easy.
I can imagine. So where in the paper do they actually get into the nitty-gritty of how they build this debut?
Yeah, they dedicate quite a bit of space to it. Pages 20 to 28, they go through the details of the construction of W. And they use three different types of solutions to do this. They've got viscous shocks, which are used to approximate the large jumps in the front tracking solution. They've got near constant solutions, which are used to mimic the behavior near local maxima and minima. And then they've got smooth solutions, which are used to handle regions where the solution is, well behaved. And the challenge is to glue these different solutions together seamlessly to make sure that the resulting W is continuous and differentiable.
So it's like they're weaving together these different mathematical fabrics to create this intricate tapestry.
That's a great way to put it.
So we've covered a lot of ground in this deep dive, from those discontinuous flux functions to those sophisticated smoothing techniques, and even the philosophical question of what actually makes a solution admissible.
It's been quite a journey, and it's really a testament to the ingenuity and the rigor of the author's work. They've really pushed the boundaries of our understanding of these fascinating equations.
We really have. But, we can't forget that nagging question that example 3.1 raised. Just because a solution is weak, it doesn't mean it's the right solution, right?
Yeah.
We still have this issue of those potential imposters, those other weak solutions lurking out there that might not actually be physically meaningful.
Right, exactly. That example, it serves as a constant reminder that we need to be careful. We need to be discerning. It's not enough to just satisfy the basic definition of a weak solution.
We need something more, right?
Yeah.
Some kind of like extra filter to help us separate the true solutions from the fake ones.
Precisely. And finding those additional criteria, those admissibility conditions. Well, that's one of the big open questions in this whole area of research.
So it's a challenge for the future, right? For mathematicians to really dig in and figure out how to make that distinction.
Exactly. It's an invitation for further exploration and discovery.
It's like we've come to the edge of the map, and now we need to chart those uncharted territories.
I like that analogy. And the authors, they actually point us in a couple of promising directions. They suggest, for example, that we could delve deeper into the properties of those viscous shock profiles, how those profiles relate to the fundamental characteristics of the conservation law itself.
So it's like we're trying to understand the footprints left by those smoothing methods to see if they reveal a pattern, a signature that points to the right solution.
Exactly. And I also suggest that we can investigate the role of the smoothing function itself, how the properties of that function, things like how quickly it transitions, how smooth it is, how those might influence which weak solution emerges as the limit.
So it's not just about the solutions themselves. It's also about understanding the tools we're using to find those solutions and how those tools might be shaping our results.
Precisely. It's all interconnected. The tools, the objects we're studying, the questions we're asking.
It's a fascinating web of relationships.
It is. And this deep dive, it's really been a wonderful exploration of that web. We've seen the power of rigorous analysis, the cleverness of those smoothing techniques, and the tantalizing open questions that drive further mathematical inquiry.
It's been a real adventure, and I think there are some key takeaways here for our listeners, for anyone who's interested in exploring this field further.
Definitely. I think, first and foremost, we need to remember that these conservation laws with discontinuous gradient-dependent flux, this is a relatively new area of research. There's still so much we don't know.
It's like a whole new continent that's just waiting to be explored.
Exactly. And second, the author's work here, it really showcases the power of those smoothing methods, front tracking, vanishing viscosity. These are not just mathematical tricks. They're tools that can give us real insights into the behavior of these complex systems.
They're like powerful lenses that allow us to see things more clearly.
And then finally, that open question about admissibility conditions, that's a reminder that the journey of mathematical exploration, it's never really over. There's always more to discover, always more to understand.
It's a path that's constantly unfolding before us.
Yeah.
Well, on that note, I think it's time to wrap up this deep dive. Thank you for joining us on this mathematical adventure, and we hope you found it as stimulating and thought-provoking as we did.
It's been a pleasure. Thanks for having me.